until 2002. After that, he was appointed as assistant professor at the Koç University. In 2012, he became a full professor at this university. He has been inducted to the Turkish Science Academy Society and has received prestigious national research awards such as the Mustafa Padlar Research Award in 2009, TÜBİTAK Research Encouragement Award in 2007, and the Turkish Academy of Science Young Scientist Award. He has held various academic positions at the Queen's University in Belfast, Princeton University, and ETH Zurich. He has contributed to a wide range of fields, including plasmonics, nanophotonics, ultra-cold atoms, quantum information, cavity QED, and more recently to quantum thermodynamics, amongst optomechanics and optical properties of semiconductors. So he has been also doing service to the scientific community by being elected as outstanding referee of American Physical Society and has written many popular science articles. So he's also currently, the principal investigator of the QUEST group at the Koç University, which stands for Quantum Enabling System Technology. Today, Professor Özgür will talk on quantum thermodynamics of topological materials. Over to you, Özgür.
Thank you very much. It is a great pleasure to listen to all these excellent talks. I have learned a lot during this meeting, and I hope I can contribute with some interesting talk, inspiring ideas to you. Thank you very much for your kind invitation, and thank you very much also, and congratulations for making this organization for all of us. So I will start. This title picture shows you the famous representation of donuts and topological materials with the topological change in a material. And at the background, you see there is heat. So we are trying to see some topological changes as well as in the presence of temperature instead of zero temperature. So this work is thanks due to my excellent students and postdocs. So this is also funded by a National Science Foundation project, which is in our National Science Foundation is called TÜBİTAK. So this is a project supported by this TÜBİTAK. And Müjde completed her studies with us and joined the University of Montreal, Canada. And Elif also contributed to the ideas and results that I'm going to share with you today. And after completion, she joined University of Malta. So currently we are continuing this study with Mohammed Tahir Nasim, who is a PhD candidate at my institute, Koç University. Koç University is in Istanbul. It is in the north part of Istanbul. I hope you can visit and interact with us. We are open to a lot of collaborations. So we are also a member of a European Coast Action, which is quantum technologies with ultra-cold atoms. So instead of real topological materials, we also consider artificial synthetic quantum simulators that can simulate spin-orbit coupling and topological effects. Then we learned a lot from condensed matter group of Professor Christiane Morais-Smith and her students, especially Sander Kempes and Rodrigo Aruca, during these studies of topological materials and their thermodynamical properties. In fact, it is Professor Morais' works that pioneered the field and showed us how to do thermodynamics with these topological objects. So the talk is organized as follows. I will give a significant some introduction, for providing some background of maybe not very common to the quantum information community. How do we do quantum thermodynamics and in topological materials, which are basically has to be finite systems because of the importance of the edge. We cannot get rid of it. So I'm going to introduce, actually these are very old concepts, nanothermodynamics, temperature-dependent energy levels. They are old but not very common. So therefore I want to make sure that everybody will have sufficient common understanding of the language I am going to use. Then after this, I'm going to summarize our results in Stan and thin film, which is, I will only have 1 or 2 slides for that. Then after that, I will go to more interesting situation of spare chain and neuronal fermions. then discuss their thermodynamical properties. After that, of course, we are not the only people that are working in this field, so I will give other examples because my talk will be limited to equilibrium thermodynamics, but there are many interesting results related to non-equilibrium thermodynamics where heat can flow, there can be multiple temperature gradients and heat paths, and again, they can be important for topological materials to understand their properties in the presence of temperature. Then I will summarize and conclude the talk. So let's start with the introduction with the topological quantum thermodynamics, what we mean by that. Okay. So why we like quantum mechanics a lot? Because it gives us a tremendous flexibility that if you look at the historical development of thermodynamics, you will see that some famous phrases that puts us a lot of limits on what we cannot do. Yes, while quantum mechanics tells us what we can do in terms of probabilities, but thermodynamics is a very solid, it has very solid boundaries that we cannot build perpetual motion machines, we cannot take temperature from cold to hot, we cannot build perfect heat engines or perfect refrigerators and so on. So in a sense, Professor Scully also said that expressed this feeling that these laws of thermodynamics makes us somewhat frustrated, while quantum mechanics and the interpretation, Copernican interpretation, gives us a lot of hope that we can go through the barriers. Like in the tunneling effect, we can have some classical boundary, but it's not impossible to go through it thanks to quantum mechanics. So the question is, if quantum mechanics and thermodynamics come together, can we make not maybe perfect, but even better engines or refrigerators, or can we do more efficient machines? This is a practical motivation of quantum and thermodynamics merging. So one example, which actually gives a lot of impetus and motivation to study thermodynamics in quantum systems, came from a series of works of Marlan Scully. I just put here one of them. This shows, if it is readable, you can check the abstract, that it shows that instead of an limits of the ideal Otto engine, you can improve it beyond using quantum effects. You can improve it beyond the classical ideal Otto limits and make it more efficient. Then you can make some machines that can be harvesting energy from resources more efficient than a classical machine. So there are many examples in literature now. You can find a lot of examples where even experiments that shows you that using quantum information also and quantum coherence and correlations, either in the work substances or in the environments, we can get a more efficient operation of our machines. So this is one example I wanted to share. So the basic idea is that we can look at a classical engine cycle and then try to find its quantum analog. This is in many papers you can see. There are also fully algorithmic, genuinely profoundly quantum mechanical cycles, but I will not consider them here, like quantum information and measurement engines. I will just consider a classical engine and look at its quantum analog. So one common engine is Otto cycle. It starts by taking the fuel injection, and after that has adiabatic compression and adiabatic expansion stages. And in between these two adiabatic entropy protecting stages, we have heating, very sudden heating, and then also cooling stages. And once the cycle is complete, you get some network output out of the cycle. So what could be the quantum analog of that? Imagine during the intake stage, if you look at this picture, here instead of a lot of particles, suppose you are allowed to take only one atom, okay? And then using single atom, suppose you have a very frictionless ideal piston, lightweighted, and suppose you can push it and make some engine. How to do this? So this all gets us an interesting analogy. So here, you can make an adiabatic transformation, which is corresponding to compression. So if you compress a particle in a box, what happens is that energy levels separated from each other. The quantumness energy gap is increasing through this compression. Okay. Well, in the expansion, the opposite happens. In the expansion, the energy levels get closer to each other. The system becomes more classical-like. More energy levels are getting closer and closer. So it's very similar to particle in a box expansion and compression. In between, you can do standard heating and cooling. So by heating, we mean that excited levels are more populated, and by cooling, we mean that excited levels are less populated, while the lower levels are more populated. This is consistent with the Boltzmann factors. So what is interesting here is that we can now forget about the classical analogy and just look at the energy levels and populations. I can use other means to change the energy gaps. I can use, for example, simply magnetic fields, take a two-level atom like a spin and use magnetic field to increase and decrease the energy levels. Or you can also use lasers to change populations as long as they match the Boltzmann distribution. So this gives us a quantum control ability to do some engine cycles without making actually a classical analogies strictly. So people did this. There is a beautiful experiment in 2016. I think it was also recognized as one of the top 10 important developments, progress mankind that performed in 2016. So in this year, remember, there was LIGO, discovery of some planetary results, etc. So among them, this was also very attracted a lot of attention. So why? Because the thermodynamics is a game-changing effect. There are like revolutionary developments in every industrial revolution. There's a thermodynamical invention. So therefore, this is actually very significant, even though it's just producing a very little work and just a single atom moving up and down in some ion trap. So here you can see this green dot, which is a calcium ion, and it is put in this red electrode, creating this separate conical trap structure. Then using a noise electric field, you can put a white noise depending on temperature, so you can assign a temperature to the atom. It's a single atom. How to define temperature is a little bit tricky, but you can use kinetic energy, for example, to understand there is some temperature in it. Then you can heat it or you can cool it periodically and look at the motion of it. And people observe that the motion in this particular trap structure is up and down like a piston motion. So they call this as a single atom piston engine. And they reported their results in 2016. It attracted a lot of attention. And this is a typical engine cycle behavior. So the red regions are where the particle is hot, and the blue regions are where the particle or ion is cold. Okay, then the area of this, like in a typical indicator diagram of an engine cycle, the area gives us the work output. Okay, so you have this closed area in thermodynamical cycle, and the area gives us the work output. The oscillations of the particle is just determined by the trap frequencies. And then this trap frequency reciprocal gives us a typical engine cycle duration. And after you calculate this area, you can divide it by this engine cycle time and find the power. And the power reported in the paper is in the order of 10 to the minus 22 joule per second. As you can imagine, this is not very exciting to build a technology or industry upon, but still it is a good start. In fact, if you compare its efficiency, that is the work output divided by the heat intake, it will be found in the order of 0.3%. Again, if you have a company, you wouldn't invest on this, but maybe this you can compare the starting point of our industrial steam revolution that Thomas Newcomen reported and did his first device in 1710, and it was also at 0.5% efficiency. Okay, so how we can start from these values and go up both in efficiency and both in power and work output are important. Of course, you can justify these results that this is just a single atom. So as an important figure of merit in energy business is how much energy you can produce or store per unit mass. So if you then divide these values to the mass of the atom, your numbers will increase. But again, you will need a lot of these atoms or ions to work cooperatively to get technologically important numbers. Okay, so the question is, if I want a lot of these ions to work together, what is the best idea? Okay, to get a higher power, higher efficiency, higher work output. Of course, I can treat them as independent workers, like a gas of independent particles, or I can make a more organized factory of workers. I can build a lattice of them. I can let them interact cooperatively and hope that the result will increase. Of course, in economy, there is always law of diminishing returns, etc. But let's forget about that and suppose that we always scale our work output with the number of particles. This is actually very well known from extensive nature of thermodynamics and free energies. So there are organized working systems like in a graphene lattice. So there are some recent papers on this. Instead of single atom engine, let's consider many body engine. And in some organized manner, in a lattice manner, like a solid state engine. This is technologically appealing, and people found that there is significant increase in the work output that in the order of milli-electron volts to electron volts. So if you compare these numbers to electron volts, you will find that since the frequency is like in the order of several hundreds of kilohertz, then you will find the work outputs like a pico-electron volt. So here, if you go from pico-electron volt to milli-electron volt to electron volt, of course, it's a tremendous achievement. So what is the other thing that we can get this organization of the lattice? So in graphene, this is not maybe too significant, but there are materials. If you have this organized workers in your system as this lattice sites, then you can increase the work output significantly. This is in fact in many situations in classical applications of energy business, we enjoy that there is a water to gas phase change engines. In turbines, we use this a lot. So in quantum physics, instead of this material thermodynamical phase changes, we have a lot of different phase changes in an organized systems, even at low temperatures, known as quantum phase transitions. Or if you go to as today's topic, you can also have even topological phase transitions, as we will see. And the question is, in similar to thermodynamical phase change advantages in the operation performance of thermal engine cycles, can we get any advantages from quantum and topological phase changes in engines in their work output? So in this case, we have to go from graphene to more interesting materials that have significant phase changes. Okay, so the idea is like in the title page. When we talk about the topological phase, we talk about the Ganus number or Chern numbers, some discrete invariants in the characterizing the properties, topological character of the material. So this is like a zero Ganus number or zero Chern number object, like a donut here. And then in one part of the cycle, instead of expansion and compression, suppose you change the topological character of the system and just open a hole in the donut. Then you heat it. Okay, it receives harvest some energy from a classical resource. Then you somehow close. This is of course not we cannot do. These are perhaps irregular situations, but suppose we find a way to close this gap before eating this. Okay, so it gets back to its original topological state. Then we cool it down, and somehow we manage to get this. Okay, of course this will be some Carnot engine. Everything will be reset. Then everything will be frictionless, etc. Reversible. But you can also design Stirling, Otto, diesel, whatever engines like that. But the key idea is instead of compression, expansion, adiabatic stages, you have this discrete number, Chern number is changing in these stages. Okay. All right, so how to deal with this? Because this topological change then requires some finite system. And this is immediately challenging us because thermodynamics are not allowing us to study finite systems. I mean, this is what my teacher told me when I took a thermodynamics course. We used this book by Kubo in graduate thermodynamics. So this is a famous author of thermodynamics and statistical physics books. So if you look at the very first pages, you will see that here that thermodynamics objects are macroscopic entities. Okay, so you need almost infinitely large number of degrees of freedom to describe these systems thermodynamically, and there is a strict statement that systems composed of only small number of degrees of freedom are not object of thermodynamics. So taking a cluster or flake of a topological field, for example, I shouldn't be able to do thermodynamics at all. Well, actually, this is not some statement. It is written in a textbook, but it is not written on a stone. So if you look at even historical development of thermodynamics, you will find that naturally people started with probability theory, statistical physics, and there were a very nice theory of large numbers. And then using this, taking the idea of Clausius and Boltzmann's entropy, you can do thermodynamical calculations, count the number of states, do the limitation as n again tends to infinity, and so on, and get the results. Yet after the Second World War, when the information became more free to share, information theory started to be flourish, and thanks to Shannon's idea. And then James used this Shannon's idea and come up with this very important principle of maximum entropy to do thermodynamical calculations. And then we no longer actually need to do this n goes to infinity limit to really get results. Even Shannon and James didn't appreciate maybe this capability of their theories, but actually this theory of maximum entropy principle doesn't require any large number limits. So how to proceed then? Still, it doesn't say us that thermodynamical laws can be directly applied to macroscopic systems because we don't know how. Why? Because the standard trivial intuitive idea of Gibbs generalization to the fundamental law. This is basically definition of heat that if you apply work on a system, there are two ways to change internal energy. You can do work on it, or you can increase and decrease its entropy. So you can have this first law here. But if you have some system of a different number of constituent subsystems that can also change their numbers, then Gibbs gives us some generalization of that. And we can use it for our calculations. And this fundamental relation is something that cannot be directly applied even under maximum entropy principle. So this term here, because it requires that definition of chemical potential, which is basically whenever you add one particle or you get out one particle from your system, there's an energy cost of doing that. And this energy cost is defined for this single particle changes. Okay. So as I can give you a counter example that we cannot write down this equation from classical nucleation theory. Suppose you have these independent particles and then they coalesce and group together and make some cluster here, some finite size, finite number of particles here. Okay. So there's a phenomenological approach which is known as the capillarity approximation to this cluster, and just we treat it like a spherical droplet. Okay. Then for spherical droplets, there are theories, old textbooks, even in 40s or 50s, these theories are available, and you can write down the free energy in these two terms. Forget about all these S sigma S1 here, they are related to surface tension and droplet physics. But just look at this n, the number of the particles in the cluster. So this part looks so reasonable that we have free energy, an energy which is extensive or proportional to the size of the system or number of particles in the system. But this second term comes from this surface. Okay, and then it is not proportional to n, so it is called non-extensive. Okay, so non-extensive thermodynamics, there are many approaches to that, from Salis to different approaches, but here we will follow a more natural, straightforward calculation of these non-extensive effects. Okay, so basically this is not applicable here. We need something else because we cannot take large and large volume limits, and properly defined thermodynamical limit doesn't exist, and we also cannot explain this term using such a chemical potential. So there's a review article if you're interested more, but let's proceed to more quantity. And the idea of the hill is following. So if I need a large number of particles, like here, okay? So let me take this as my system. But suppose I want to do thermodynamics, but instead of looking at a single cluster, single nucleated cluster here, imagine there are infinitely many of them. Okay, so we make an ensemble of these clusters. Here I just show you three particles, but it could be larger cluster or smaller cluster, but it has fixed volume, fixed number of particles, and every copy is just identical replica of the other. Okay, so there are identical copies, and moreover, it's an ideal guess. They are not interacting with each other. Okay? So then we can make that such an ensemble. So how to use this ensemble to learn about thermodynamics of a single system? This is the basic main idea of the Terence Hill, and it's a very clever idea. So it starts that I can write the fundamental Gibbs equation for a macroscopic system. Okay, so this is my ensemble of particles. So imagine I have my nucleated cluster of n atoms. Here I just took it for simplicity like a cluster, like a chain, but you can take other networks. So each volume here represents one big, not thermodynamically big, but some number of atoms inside, some cluster inside. Okay, so this is my ensemble. And from this ensemble, I'm going to build a large system. So I can take one system and inject it into the system. And the way to do this is to apply some pressure and inject the system at some pressure known as, just call it as integral pressure. Okay. Then the natural way to also, whenever you add one particle here, because now these are finite volume objects, whenever I inject a finite volume object to an already crowded system, I am increasing with its volume. Okay. So here you can see there is some volume increase by putting more and more particles here, more and more systems here. And let's say that this calligraphic n shows a number of systems which were already existed. Then when you put more and more, you get a change of the n multiplied by volume. So this is my term. Multiply this volume change. This is the total volume change after the n injection. If you multiply it by this integral pressure, you will get some term hidden in this x. Okay? But suppose there is another way of enhancing the volume. I can add more particles to my cluster. Nucleation can continue. Then the volume of the cluster can grow. Okay? Instead of 4, maybe you have 5, 6, so it can change as well. And the pressure cost of doing that, let's say, is standard pressure P, so that the contribution of the existing n particles, n clusters in the system, each changing their identical replicas and each changing their volumes by dV, okay? Then multiply it by the pressure, you get the work done on the system, okay? So you have integral work done on the system, and also you have some standard work, mechanical work done on the system, in addition to heat changes and chemical number particle changes in the system. So these two are standard Gibbs methods, Gibbs approach to internal energy, and these two are just addition results. So what's the advantage of doing that? You can start with this expression, standard Gibbs expression, because now we are allowed to do thermodynamics, because this system is infinitely large, macroscopic. Then you can start with this. Then you can assume that, suppose my ensemble is just a canonical ensemble, grand canonical ensemble. So its volume is constant. Okay? So I ignore now this particular dV change and drop this term. Okay? And then I start with this Gibbs equation. Only integral pressure term remains. Then I just integrate this because classical thermodynamics, and I can integrate for this constant x, mu, and t terms. After integration, I get the standard internal energy relation. Okay? But here, the idea is now this is for the entire system. And I can now assume that the particles or the systems are identical replicas of each other. So taking ensemble average is simply equal to dividing the system by the number of subsystems in it, okay, the number of replicas in it. So after this division, you get this equation. But here, if you take it as derivative with respect to variables of entropy, n, and volume, and write it in differential form, you will see that these two are not related to each other through earlier integration. Okay? This is not integrable anymore because here the epsilon, or so-called subdivision potential, is the difference between the full unbounded ensemble minus a bounded ensemble. Okay? And this is the main idea, that the logical idea behind the Hill's approach, to build a large ensemble and make an ensemble average to talk about single system. Okay? Then using the energy and its differential expressions, you can look at how the subdivision potential differential changes, but this is nothing but a Gibbs-Duhem relation, because it gives us temperature, pressure, and chemical potential differential relation. Normally this should be zero, but here we have now a finite term. This is coming from the difference between unbounded and bounded systems. Okay? So using the definition of subdivision potential, you can also find the differential of the X, and you can see that this is exactly the same as the thermodynamical equation. So this teaches us how to use thermodynamics for this system, and then we can see that this equation here also identifies what is X, this unknown X introduced by this clever idea of the Hill. But this is nothing but the grand canonical potential, because right-hand side is exactly grand canonical potential expression. Okay? And this gives us a microscopical notion of subdivision potential, that if you recognize this X as a grand canonical potential, so pressure and the volume multiplied, but this pressure is extra because of the finite volume systems are injected at some cost into the full system. Then by just making Hamiltonian relation for the grand canonical partition function, you can relate the microscopic statistical nature of the system to these Hill's introduced variables. And this is how we deal with finiteness of our system. But this is not the only approach. There is also temperature-dependent energy levels. And you see these are again very old ideas coming from 40s or 50s. Okay? So I just don't go over history, but again tell you the basic idea. So what is missing in the Hill's approach is that we do not know how these subsystems can be kept at the same temperature and how to define temperature for them. So alternative to Hill's idea to explain thermalization of small systems, we talk about, instead of looking at this cluster, nucleated cluster of particles, we make, instead of building a gas of small clusters, let's imagine we add additional subsystems and make this cluster infinitely large. And treat these systems, they are already semi-infinite, so we can assign temperature to them. And then we can treat this whole problem as a thermalization problem of a small system, some reduced subsystem of a full infinitely large system, and do thermodynamics for this case, for the large system, and then get the reduced system. But when you go to reduced system, what we know from quantum mechanics, we use these partial traces. Okay? So we trace over these added subsystems to talk about the thermal properties of the small subsystem. Okay? So B refers to these gray areas, which we call interfaces. So if you trace out the interfaces, you get thermodynamics of the small system. But if you do this, you have now several options. You can say that this picture can be mapped to some exponential decreasing form to make analogy to the Gibbs distribution. Or you can say that my Hamiltonian is time-dependent, and it is equivalent to, again, some effective Hamiltonian with time-dependent property, not time, of course, temperature-dependent. So these two are known, one of them is known as temperature-dependent energy level approach. The other one is known as Hamiltonian of the mean force. So there is some literature for independent literature. This is older idea, and this is more modern approach. So after you do this, this is not unique. You can put here sinusoidal function, you can put here linear function. So why do we choose exponential function? Okay, so when you choose exponential function here and do thermodynamics, you will find that you are able to write free energy exactly as in the case of Helmholtz free energy expression of standard thermodynamics. So we choose this form for making sure that out of indeterminate choices, to make sure that we can have standard thermodynamic expression for free energy. But the cost is that we cannot put every thermodynamical function in a standard form, in a macroscopic form. If we fix free energy in standard form, then if you look at the entropy and mean energy, you will find that they are no longer in standard form. So standard form of the mean energy is probability multiplied by energy and sum over all states. entropy is just the summation of probability multiplied by logarithm of probability. Okay, but there are energy dependent terms that depends on temperature derivative of your effective energies that depend on temperature on this form. So I have two additional terms in mean energy and entropy of the system. Okay, so these are still exact. You can do, they only have this partial trace operation, pure averaging of the system and interfaces getting ridden off. So these are exact expressions, just to help us to do calculations a little bit easier. Okay. So let's write this in compact form. Again, I am writing mean energy here, the new term and probability contribution standard term. And I can write this because of this averaging here. I can use it a more compact expression. Okay. So mean energy requires this Hamiltonian mean force contribution. Now for the Hamiltonian, you can again from here take it as derivative and write it in differential total differential form. And you can see that this is standard quantum thermodynamical expression where we can define the work and the heat, but there's an additional term. So it's a generalization of the quantum thermodynamics to finite systems with interfaces. Okay. So again, from the entropy, you have such an expression, and you can take such generalization of the second law in the case of interfaces. So we have first law and second law results in a nutshell here. What is the meaning of this then? If you write down the first law for a finite system with interface, you have this additional term. So one of the terms are just standard heat term, this TDS. The other one is standard work form. But let's assume that there is no work done on the system, only some bet is attached to the interfaces, and the middle system is just thermalized. Then this heat coming through the interfaces is lost. Actually, some of them is lost in the interface. And the middle system in between interfaces only receives some of this heat. And we call this as the effective heat. So we cannot perfectly transfer all the heat into the system. Some of them are just spent as a work done on the interface, because temperature and energy levels also change during thermalization. The energy gaps are changing by temperature in this approach. And therefore, when you change energy levels and their relative separation, you are doing work on the system. So the heat pad not only actually transfer heat into the system, but do some work on the interface to adjust energy levels and populations for proper thermalization of the system, of the finite system. Okay, so these two systems are connected to each other through statistical relations. So simply we write down the entropy and compare it with the heat's energy. Okay, so in this entropy expression, if you just substitute our definition of the temperature-dependent energy levels for a ground canonical ensemble, we also have chemical potential contribution here. So if you substitute it and write it down, you will find that this is the mean energy. And we compare this mean energy with the expression of the hill that he has found, which has this subdivision potential, main ingredient of the Hill's thermodynamics. And this comparison of these two expressions allows us to identify subdivision potential does the same job as the temperature-dependent energy levels. Okay, so these are two different approaches. One of them assumes there's an independent ideal gas of systems to talk about thermodynamics, then make ensemble averaging to talk about thermodynamics of a single system. The other one takes a single system, extend it to infinity, but then these two are nicely connected with this expression. Then we can use this both the fields approach and temperature-dependent energy levels approach together, contributing us to write down the effective heat during the energy exchange between a system and a heat pad. So we can also identify the second law by comparing with the information channels, the interface. So interface acts like an information channel actually that is doing coherent work to adjust its energy levels, while this one is incoherent part in this information exchange and heat exchange. So therefore, you can compare this with generalize the second thermodynamical law of communication channels. Okay? So you can look at this reference. It talks about how the second law in the case of information channels is applicable. All right, so we have these formalisms, and I will just summarize our results. So we first look at two-dimensional thin film of a stenon. Why stenon? Because it's some material with large spin-orbit coupling. It's belongs to the family of silicon, germanium, and stenon. So basically, don't worry about this solid-state motion here, but it is just an organized set of workers. Okay, in two dimension, this is my factory, and these are my workers organized. And what is nice that if I apply some electric field into these workers, I can control the topological character of system. So I can have donuts or I can have standard bread, like a nun. So here, beyond a certain strength of electric field, it becomes a topological insulator, and before that, it becomes a standard band trivial insulator. Okay. So what we have observed here is that we can make a topological change during this cycle, energy cycle, as was explained, and then the maximum work output coincides where the topological change occurs. Okay. So I can just use a non-topological change, standard electric field increase and decrease during the adiabatic stages. So it starts with trivial insulator, goes to trivial insulator. It starts with topological insulator, goes to topological insulator. Then I get some work, but this work is not interesting, not very strong. But if I allow a topological change, the work is the maximum. So moreover, if we calculate efficiency here, I didn't show it, but efficiency also becomes maximum. So this is a nice practical appeal that we have maximum work at maximum efficiency, and both of these maximum coincide where the topological change happens. Okay? But our study here was limited to low temperatures. So just a few days ago, Professor Kumar and Professor Benjamin, they just published a report on arXiv recently, and they have found similar pictures, not for stenon, but for some generic flow-cut topological insulator. And they have found again the phase transition happens in this phase transition happens at the maximum work and maximum efficiency, but nicely this can happen at much larger temperatures. So we are not limited to low temperature regions that we have considered in this picture. So this is basically this shaded area shows the parameter regimes where the high and low electric fields are applied, or in our case, this is positive work regimes. And these are the churn numbers, which shows that in the engine cycle, there is a shift. There's a discrete shift in the adiabatic stages. Okay, so what is missing here is that how the edges after topological changes contribute to the work output. Okay, so to study this, 2D is not a very good choice. It's too complicated, but let's consider one-dimensional topological material, which is a QFTA chain. Okay, so we have superconducting gap parameter, hopping coefficients, and when this superconducting fixed number, then looking at the chemical potential, if this chemical potential is equal to 2 times the hopping parameter, you have a phase change. A churn number makes a discrete jump. And when this happens, Majorana fermions appear at the end of the QFTA chain. Okay, so we look at, we start with a standard QFTA chain in trivial phase. Okay, then change its churn number by playing with the chemical potential. Then heat it and then change churn number back again and then cool it and make a cycle. Okay. So we just use, as I explained, Hill's approach to separate the bulk and boundary contributions. Okay, so the subdivision potential here is now denoted by phi 0 to make it more similar to ground canonical potential. This is basically the potential difference between the bounded and unbounded chain. Okay, so this is our subdivision potential. So if you start with this such a ground potential and just calculate entropy as usual, that means that entropy is also separated in 2 parts. So you can easily separate the bulk and boundary contributions. Okay. So therefore, we can calculate what is happening in bulk and edge or the end of the chain using these 2 new entropies. And this allows us to identify the contributions separately. So this is a 200 hundreds of sites long chain with some, we are using here natural units where all the natural unit constants, fundamental constants are 1. So given different implementations of the QFTA chain ranging from superconducting circuits to ultra-cold atomic optical lattices, you can have different numbers, units here, but basically these are toy variables. Okay? So we look at the, first of all, the bulk system where the entire chain is imagined, and it goes through some constant entropy changes. And in between constant entropy changes, we have different chemical potentials and heating and cooling stages. So this A, B, C, D defines an Otto cycle. Okay, we have isentropic stages, these are adiabatic stages, then heating from A to B and cooling from C to D. So 1, 2, 3, and 4 are consisting of 2 adiabatic and 2 isochoric, that is isoparametric changes on the system. So from A to B, you can see there is a positive heat, and the sign of the heat means that there is a heat intake. Positive heat means there is a heat injected into the system, and negative heat from C to D, that means heat is rejected from the system, and in between we have the work output, okay, which corresponds to, for our chosen parameters, corresponds to maximum work, corresponds to topological change of the system. And efficiency also shows that the maximum efficiency happens again, like in the case of Stener, at the maximum efficiency, maximum work, they both coincide with the topological change point. But here everything is the full chain. There is no bulk and edge separation. So if you look at the bulk cycle, it is very complicated. So here A, B, C, and D are connected through these changes. So temperature first increases and then decreases during the adiabatic changes. So adiabatic change is no longer adiabatic. Okay? So while the entire chain goes through Otto cycle, in fact, before and after the phase transition topological point, the bulk of the system, that is not the edge, but just the bulk of the system, goes through some non-adiabatic cycle. Okay? To understand if this is a heat engine cycle at all, we have to look at the sign of the heats during the stages, and we find that this cycle can be identified as an non-ideal Otto cycle. It's an engine cycle, both in the trivial and topological phases. If you look at the boundary cycle is also showing you that it is highly deformed Otto cycle. But still, if you look at this cycle from A to B, B to C, C to D, A, and this is already deformed Otto cycle because entropies are no longer constant. This is the edge entropy. So therefore, there is no adiabatic stages. Okay? So if entropy is not uniformly zero change, then of course this is non-adiabatic. Okay? And if you look at the signs of the heats, you recognize that there is a refrigerator cycle for the sign of the heats for the topological phase, and there is an engine cycle before the topological phase. Okay, so in the bulk we have engine cycles, but in the boundary or in the edges of the chain, we have before the topological phase transition, we have the engine. After that, we have refrigerator. So character of the cycles are quite different, and how to explain that. Okay. So first of all, when you do not have the entropy constant during adiabatic transformations, that means that the end of the chain and the bulk of the chain or middle of the chain exchange some entropy, because entropy of the total chain is constant because it goes through adiabatic change. And we have this equality that there is a sign change. So heat goes from one part of the edge into the bulk, okay? And in the other transformation, it goes in the other direction. So there's a heat exchange. If you, in terms of entropy, you can look at the heats. There's a heat exchange during the adiabatic stages between the bulk or the middle of the chain and the end of the chain. And this is actually very similar to what happens in adiabatic transformation if you try to do it in a finite time. So normally, in adiabatic transformations, you want a perfect state transfer, that there should be no population transfer between the energy levels. If you want to do it, then you have to do it very slowly. If you do it fast, then you will build up some coherences and destroy adiabatic requirement. And here what we see is the spatial analog of that. In ideal adiabatic transformation, I will need infinitely large macroscopic chain to make perfect thermodynamical adiabatic transformation, but now I have a finite chain. And therefore, because of the finite chain, because of the difference between bulk and edge, I have entropy change between them, and therefore they cannot go through ideal adiabatic paths, and their parameter space are sliding on each other. This is actually a definition of friction. Since Leonardo da Vinci, tribology means that in some path we have relative motion of two objects and there is friction. But here the edge modes and the bulk modes are going through parameter space that I am making transformation adiabatically, and because of the relative parametric motion, I got some friction that we dubbed as internal geometric fluid. So to compare the effect of edge and the bulk more clearly and talk about whether these gap closings and phase transitions are really topological, we compared some effective Hamiltonian of the behavior of the Majorana fermions. So we just take two fermions, coupled fermions at the end, and write down a Landau-Zener model. So what happens that if there is no G interaction, no coherence, then we have level crossing. If there is G, we have avoided level crossing. So there are two ways to cross this gap. So one of them is how the bulk is closing the gap. The other one is how the edges are closing the gap. So if you compare this, you will find that, again, in this avoided crossing, you have in maximum work in certain frequency, that is when the level crossing happens. But in the boundary, you have a more smooth maximum of the work. Okay? So if you compare it with the behavior of the bulk and the ends of the Kitaev chain, you will see similar qualitative behaviors. So we can justify that in the Landau-Zener at zero temperature, we have quantum phase transition. And it happens similarly here in the case of Kitaev chain. So how we can compare zero temperature quantum phase transition to finite temperature topological phase transition? This is a little bit technical issue that, first of all, actually, when you look at this, there is a specific heats, and we are actually doing at finite temperature some difference of the specific heat because entropies S0 and S are different for the bulk and the edge, and specific heats are different for the bulk and edge. And this is like a thermodynamical F phase classification of the phase transitions. But in the case of Chern number, we have the geometric phase, Berry phase to define them. But at finite temperatures, it's possible to generalize, as long as the temperature is not very high, generalize the Berry curvature to so-called Uffman phase, Uffman curvatures at finite temperatures. So at low enough temperatures, again, this F phase classification of thermal phase transitions are usable for topological phase transitions. And moreover, this tells us to understand topological phase transition and gap closing. It's not enough to just look at the whole chain. You have to look at the edge and the bulk differently. And what you have to see is you have to have a different order of phase transitions at the edges and at the bulk. If you can see this different order, then you can conclude that this is a topological phase change. Okay, and also we have included the interface effects and calculated the how the interface reduces the work output, because some of the heat is rejected and dissipated as a work at the interface. And also during the rejection stage, you have to reject more heat from the system to again work on the interface. So therefore, your work output reduces. It's not a big quantitative change. So the presence of interface will not influence much the experimental observations. This is our conclusion. So to give you more ideas about the topological effects, there is also what the talk is limited to equilibrium thermodynamics. There are also studies of non-equilibrium thermodynamics using heat flows. So if you want to heat some object with boundary.
Sorry to interrupt. We are running a bit late, so maybe if you can quickly run through this. Thank you.
All right. All right. So basically, these are other people's work. So I just wanted to give them credit for. So there are heat flows also that can be used to study topological effects. So you can have a variation of heat flows at the edge and at the bulk, which counterintuitive and challenging second law. And they can also be used to use Majorana fermions to build some heat diodes, heat transistors using Majorana fermions because of their non-trivial heat flow effects at the edges. Okay, so this is my conclusion. You can read it from here. I don't have to repeat it. So thank you very much for your attention and for your patience. Thank you. That's all.
Thank you very much for this nice and interesting talk, for introducing new tools and methods to study quantum thermodynamic systems. Now, though we are running a bit late, but maybe we can take one quick question from the audience. If somebody wants to ask a question or make a comment, can do that.
Hello.
Yeah.
Thank you, Professor, for the talk. So I have one small doubt. So since you showed that your efficiency is maximum at the boundary of two topological phases, right? So do you think we can consider, or we can consider the efficiency as a parameter to detect topological phase transition in these materials or in other materials?
It's a very good point. So here my focus was to increase the performance of the engine. As I said, you can look at this point, but you have to look at it both for the bulk and edge. So you have to make measurements both at the bulk and the edge, maybe using special gates on the system, on the topological system. And to conclude, really, this is not only simple gap closing, but a topological phase transition. You need to see one order of difference. So one in the bulk, it should be second order. In the edge, it should be first order phase transition. So if you see this different order of phase transition in the bulk and at the edge, if you can observe it, you can conclude.
Okay. And then
the measuring efficiency is not enough, but you have to look at efficiency both at the edge and at the bulk, and you should see qualitative differences in both cases.
Okay.
Yeah, I will suggest to continue the discussion if you want to in the chat box.
Of course. Thank you very much.
Okay.
Thank you.
Yeah. So let's thank Professor Osgar once again, and we move on to the next speaker. Our next speaker is Amit Devra. He's a former alumnus of ISER Mohali. He did his BSMS degree from ISER Mohali in 2018. And currently he is a Marie Curie early stage researcher working on the project Quantum Enhanced Sensing via Quantum Control. He is working in the group of Professor Stefan Glaser at the Technical University of Munich. Okay, and today he's going to talk on Wigner process tomography of unknown quantum propagators. So over to you, Amit.
Thank you very much. Can you hear me?
Yeah.
Okay. Thank you. Thank you, Professor Johal, for a nice introduction. So as Professor Johal said, I'll talk about the Wigner process tomography of unknown quantum propagators. This work has been done during last 2 years of my PhD in Technical University of Munich, and this work has been done in collaboration with Niklas Glaser and Stefan Glaser. So let me introduce what QSCO is, the project that I'm working on. So it is basically quantum enhanced sensing via quantum control. It's a project under the European Union's Horizon 2020 program, and there are 15 project partners, including both academics and the industry. And I am currently working in Professor Stefan Glaser's group. So let me begin my talk. So first, I'll talk about how to visualize the operators, the quantum operators. So an operator A, which can be visualized by mapping given by, so that the operator A can be broken down into the rank components, which is AJs, and then can be simultaneously mapped to the spherical functions Fs. And more explicitly, the mapping can be done if you break down the rank J operator A into the irreducible tensor operators TJM with some coefficient CJM, and these can directly be mapped to spherical harmonics YJM. And this work has been done by Stefan's group in 2015. So these are really nice visualization techniques. So this is an example of how the visualization works. So here you have a two-spin system, and the system of this, the spin system is given by this operator A, which is so this the spin 1 is in the X direction that you see here, and then the spin 2 is in the Z direction that you see here by these nice drops representation that we call them. And these are the bilinear operators, or the coherences, the bilinear terms that you see here. And then put together, the two-spin system for this particular state looks like this. And this corresponds to the identity operator, which is in the front of A. And just to give an example how the drops representation works and how one can visualize these the spin, and to study the spin dynamics, we have this software called Spin Drops, and I'll show you briefly like how this works and by an example. So here you have a two-spin system. So I'll show you the example of the polarization transfer from spin 1 to spin 2. So here you see that the density operator over here, that the spin 1 is in the Z direction, and after the application of these pulses, which in NMR are simply known as the inept pulse sequences. And here we'll see the propagators over, which is the time evolution operators over time. So let me just play this video. And then you see that as the pulse sequences are passing, the time evolution, the density operator is changing and the propagator is also changing, and the polarization has been transferred directly from spin 1 to spin 2. So this video has been taken from Spin Drops, which is a very nice software for visualizing and studying the spin dynamics. So sorry, I don't. Yes. So the next question that comes to our mind is, can we experimentally recover these Wigner representation, or these are some abstract mathematical formalism? But it turns out that we can do this, and so it can be simply achieved by calculating the expectation value of these rotated axial tensor operators, Tj alpha beta, and then the operator of interest A. So in this case, in the quantum state tomography, the operator of interest A will be simply the density matrices. And these are some constant factors which are dependent on the rank of the operator, and the definition of the expectation value is simply given by the trace formalism here in equation 5. And this work has been done by David in 2017 in Stefan's group. So pictorially, it looks like this, that the tomography scheme that we have for the Wigner in the Wigner context. So you have you can consider these operators inside a block sphere, a closed system, and the red arrow that is shown here is basically a sensor. So your system is like this, and you rotate your red arrow, and you calculate the expectation values at every possible angle, alpha and beta. And in the end, you will you plot these drops, which is simply the spherical functions on the right, and then you can reconstruct these shapes that I showed you before. So this is simply can be done by quantum state tomography. And so the next question that comes to our mind again is that is it possible to use the same scheme for the propagators? So it is possible, but the problem is the approach that I showed you is for the Hermitian density matrices. So the problem is possibility to map the unitary propagators onto the Hermitian density matrices. In order to do that, we have this is a scheme that has been worked again, like in Stefan's group. So what you need to do is perform a control U kind of operation, where I0 is the control ancillar spin, and then I1 to In are the system spins. So you perform these kind of control U propagators in order to map the unitary propagators onto the Hermitian density matrices. I'll show you by a quick calculation how that can be done. So you have this system here that we want to see, and the control U, the propagator here is given by the identity on the top diagonal element and the unitary propagator into the lower diagonal element. And the initial density matrix is chosen in such a way that the I0 is in the superposition of up and down qubits, which is 0 plus 1 by root 2, simply Ix. And the other system spins are in the mixed state or maximally mixed state, which is the identity. And after the application of these control U operations, we have something kind of this as the final density matrix, which you can see that we are able to map these unitary propagators into the off diagonal elements of the density matrix, and the density matrix is overall Hermitian. And this can be easily, this work has also been done in 2018 by Stefan's group. So here comes my work. So my work was to investigate the same scheme for the unknown propagators. So if we don't know anything about the propagator, can we still tomograph these unknown operations? So since the problem that comes here is that since the propagator U is unknown, hence control U is not possible. And like moreover, we are also prevented by the no-go theorem. At the bottom, you see that this theorem suggests that it is not possible to control the unknown quantum operations when the operator is only used once. But this has not stopped people from performing these operations. And I'll show you some of the circuits that has been well known for controlling the quantum, the unknown unitary. So here, what system you have is the I0 as the control qubit, and I1 to In are your system qubits, and I1 to INA are again your ancillar qubits. So in this case, you have 2n plus 1 ancillar qubits, one being the control and the other n the ancillar qubits. So you perform these swap operation, control swap operation, and this control swap operation only works if you have I0 is in the up state, and doesn't work if it's in the lower state, or that means 0 or 1 state. And then you perform these unknown unitaries, and then you swap back the information. And in the end, you partially trace out these ancilla qubits. So you are back in your system qubits, and then this is a pseudo like control over the unknown unitaries. But this works really well for the classical controls. What I mean by that is the I0 is in either 0 or 1, then it works really perfectly. But it doesn't work if the I0 is in the superposition of 0 and 1. That means if it's in the quantum control. So if it's in the 0 plus 1 by root 2 or in the IX state, then after this operation, the system qubits and the ancilla qubits gets entangled. And if we do the partial tracing out of the ancilla qubits, we'll lose some information. So it is not possible for doing it for the quantum control. So for our application, we have designed or we have proposed our new circuit for controlling an unknown unitary for tomography of unknown quantum propagators. So what we do here is that you have the similar circuits as before until here, that your I0 is your control qubit and system qubits are I1 to IN, and then I1 to INA are your ancilla qubits. And these are the control swap operations. Then you have the unknown propagator and control swap, which is also known as the Fredkin gate in general. And this is the control R operation that you need to perform on the ancilla qubits. And the maximum number of control rotation operation is 4 to the power of n. And for single qubit, n equals to 1 system, the control this rotation operation is simply a set of identity sigma x, sigma y, and sigma z. And we are not violating the no-go theorem in this case, because we are not using the unknown unitary only once, but we are using more than once to get all the information of the propagator. So next, I'll show you the calculation of how are we doing this. So the initial density matrix that I showed you before in this circuit is simply a superposition of 0 and 1, I0, and then I1 to IN, and all other spins or all other qubits are in the maximally mixed state, which is given by the identity power 2n, or like 2n, which is simply the dimension of the system. So after the action of the full circuit until here, so this is the final density matrix, where k is the index of the control rotation operation. So you have different control rotation operation, and then you perform this circuit to receive to get the final density matrix. So for n qubit system, the final density matrix after tracing out the n ancilla qubits looks like this. So after tracing out these n ancilla qubits, we are back in our system, which is n plus 1 spins, 1 being the control spin. So we are back in the n ancilla qubits. So here you see, in comparison to the known propagators, we are able to map these unknown unitaries onto the density matrices, but with some with some scaling factors, epsilon k's. And these epsilon k's are dependent on the kind of control rotation operation that you're applying in the last. And these are dependent on the matrix elements of unknown u. So let's look at how these scaling factors looks like for different control rotation operations. So let's say that a single qubit system, this is a single qubit unitary that can be represented by this. And in terms of quaternion, one can write in terms of the quaternions A, B, C, and D. And the scaling factors looks like are dependent on the control rotation. So these are the scaling factors. And remember, these A, B, C, Ds are unknown to us. And the resulting propagators that we get in the end are basically the scale version by these scaling factors, like I times A and I times B, dependent on the different control rotations. So in order to take care of these scaling factors and to reproduce your full unitary propagator, we have designed a reconstruction algorithm whose aim is to estimate the quaternions A, B, and C, and D to reconstruct a propagator from a given set of experiments. So this is a pictorial or like a flow chart version of the algorithm. The full algorithm has not been published yet, so I'll just present the flow chart of this. So you have a unitary propagator which is unknown to us. You perform k experiments. You pre-process the data. You reach a state which is V cap, and then dependent on the experimental data. And from these sets of experiment, we actually estimate the zeroth estimation of quaternions A, B, C, and D. Then we pass it through the iterative step so that we refine these propagators. We refine the value of the quaternions. So this is the preparation step, and this is the iterative step. So I'll show you one of the examples, or before moving to that. So this the algorithm terminates when the change in the value of quaternion A, B, C, and D is not significant over the iteration. So when the change in the I'll show you by example as well when is this algorithm gets terminated. So I chose an example for a single qubit system. So you have a Hadamard gate, which the matrix representation of which is given by this, and the drops representation of which is given by this. So you see like two drops on the x-jet plane, on the diagonal of the x-jet plane. So the Hadamard gate, the ideal case, so these are the scaling factors that you see, like, here, dependent on control rotation x, y, z, and identity. So for x and z, you should see the scaled version of the Hadamard gate, which is scaled by 0.071 in this case, and similarly in this case as well. And for Hadamard plus control y and control identity, we don't see anything because the scaling factor is 0. So this is the ideal simulation results. So I'll show you, like, if we introduce some noise into the data, you'll see some of the factors which were non-zero here, but we are seeing some factors here because this is because of the 10% noise in the data. And you also see some ripples or like some discontinuity in the drops. And similarly here for the 20% noise, you see that these errors are getting bigger and bigger, and similarly in this case. And for 35% noise, you see that these drops looks like the exploded drops or something like this, and these are the noise terms again. So we passed these there's 35% noise results to our reconstruction algorithm, and we see that in the figure 1 and figure 2, the dashed lines here are these the ideal value of the quaternions, and the solid lines are actually how the quaternions are proceeding over the iteration. So like how is it changing over the iteration? So you see, like, these quaternions A and C are going, the value of the quaternions A and C going towards the ideal value after some iterations, and similarly for B and D. And since one of the criteria to stop this reconstruction algorithm is the changes per iteration, so you see after the third or fourth iteration, or even like before that, it's one can stop the iteration because the changes in the value of the quaternions over the iteration is not very significant because it's in the value of 10 to the power -3. So in figure 4, you have the calculation over, this is the fidelity calculation over per iteration. And this is the fidelity calculation with the ideal Hadamard gate. And you see, like, the reconstructed operators in the first iteration is very close to the ideal one, and then in the subsequent iteration they are pretty close to the ideal one. And this is one of the drop that is being plotted for after the 6th iteration, and these are the reconstructed drops, and the fidelity of the plotted droplet is 0.99965. So in this case, like, or in this way, like, you can see that we are able to reconstruct these unknown propagators from some experimental data. And these were the simulated results. And next, I'll show you some experimental results that I performed on NMR as well as on IBM-Q. Before that, I'll show you some theory work that. So, in order to reconstruct these propagators experimentally, we need to calculate these spherical functions for different angles beta and alpha, and these can be calculated by the expectation value of these operators and these operators. And these are simply some constant factors. And the axial tensor operator is rotated by taking the axial tensor operators and applying some rotation operators R alpha beta in this case. So for a single qubit system, this is the circuit that we need to perform in order to do it experimentally. So you have I0, I1, and I1A. These two are the ancillary spins. You have control swap, unknown propagator, control swap, and these control R experiments. These are identity X, Y, Z. And these are the rotation operators that I showed you before, that we need to rotate the we need to rotate the system so that in order to do the tomography for different angles. And in the end, we are measuring both the control and the system qubit. So for single qubit experiment, J equals to 0, the rank 0 and the rank 1 component can be simply obtained by measuring these values, Ix, Iy, Ix, I1z, I0y, and I1z. So we actually need to calculate these 4 expectation values. And in NMR, these terms are directly these terms are directly measurables. We don't need to convert them into NMR measurables once again. So these are very simple experiments. I mean, in a way, these are very simple experiments, but the only problem is that the application of these control swaps that you're performing. And these control swaps are really complicated. I'll show you how I perform these experiments. So in order to do the NMR experiments, which were performed on 600 megahertz NMR spectrometer at BNMR set in TU, Technical University of Munich. And the sample that we used is fluoromelanic acid, as shown here. And the spectrals were measured in 5 mm Shiogemi NMR tube to minimize the errors due to B1 inhomogeneity. And this is the sequence for control swap. As you can see, there are so many pulses, like spin 1, spin 2, and spin 3. And to perform the approach that we designed, we need to perform these control swap experiments twice. That means that we need to repeat these pulse sequences twice to do this. And the initial sequence was actually designed using the average Hamiltonian theory. And but these were not robust against different kinds of errors, such as amplitude fluctuation for different channels. So in order to do that, I used my master's work, which I did with Dr. Kavita Durai and Professor Arvind at IISER Mohali. And I used the genetic algorithm in order to make these sequences very robust against the amplitude fluctuations. So here, the blue curve is the robustness curve for the original sequence that we designed using average Hamiltonian theory. And the red curve is basically the optimized sequence, or not the optimized sequence, but we use the original sequence and we just try to optimize that for the robustness. So you see that the next sequence was for relative amplitude fluctuation up to 30 plus minus 30%. It's quite robust. And to show you another robustness figure, so this is the robustness figure for the relative amplitude fluctuation and the offset. So you see that at least in plus minus 20%, the fidelity of the sequence was quite high. So we use the sequence to perform the operations or the approach that I just discussed. So these are for operations that you have, so these are the expectation values like Ix, Iy, Ix as shared and Iy as shared for different control rotation experiments. And in this case, this is the another case for the Hadamard case, the experimental results. So in simulation or we shouldn't see here because the scaling factor was 0. So we shouldn't see anything here and here, but we should only see these results only here and here. And these should be scaled by the values of the quaternions. And we passed these results through this reconstruction algorithm. So for figure 1 and figure 2, you see that again the dashed lines are the ideal values of the quaternions for the Hadamard gate, and these are the solid lines are the reconstructed values of the quaternions after every iteration. And you see that these are really going towards the ideal value in this case as well. And the changes per iteration is smaller after let's say 6th or 7th or 10th iteration as well. Oh, sorry, the 9th iteration. So we can there was the stopping criteria for the algorithm. And this is actually the figure 4 is the comparison for with the ideal Hadamard gate. So you see that we are in the subsequent iteration, we are going pretty close to the ideal Hadamard gate. And this drop on the right is plotted for the 6th iteration, and the fidelity of the plotted drop is 0.9875. So, these results were not very up to the mark. We are pretty close to the ideal Hadamard gate, but these are not up to the mark because of some systematic errors in the NMR experiments, because these NMR experiments are quite big, and we couldn't nail down the particular problem of doing these of the errors in these experiments. So we also performed these experiments on the IBM Cube on the NISC device. So you see that that this is the circuit that we need to perform on IBM-Q for our approach. And these are the two values that, for the rank 0, we need to reconstruct the F00 and then F11 for the rank 1 operators. And these are the terms that we need to measure. And since it's not an ensemble ensemble quantum computing, it's a pure state quantum computing in IBM. So we need to we transform these circuits so that one can directly use it in the in the IBM. And the experimental details are as follows. So we use the device called IBM-Q Casablanca, which is 7-qubit, which has relatively less error for control knots and single qubit unitaries in comparison to the other 5-qubit or other devices. And in this case, we use the resolution in theta was 6 values between 0 and 2 pi, the rotation operation that I showed you. And similarly, the resolution in phi was 12 values between 0 and 2 pi. And we performed this 4,096 shots on this device. And these are some the unknown tomography for IBM-Q results. And these are again Hadamard plus control X, control Y, control Z, and control identity. So you see that here you get some signal, and then these are the Hadamard plus control X operators, and then these should be 0. So as they are, but these are some noise factors that you're seeing here. And similarly, in this control X and control Z, we are pretty close to the Hadamard gate in advance. So we passed it through the reconstruction algorithm that we designed. And as you see that in figure 1 and figure 2, again, these reconstructed values of the quaternions are going pretty close to the ideal value in the dashed line. Similarly, in the figure 2 as well. And the changes per iteration over the iteration is not very significant after 6th or 7th iteration. So we stopped, so there was stopping criteria. And this is actually the fidelity comparison with the ideal Hadamard gate. So we see that in the first iteration, we are pretty close, but in the subsequent iteration, we are getting very close to the ideal Hadamard gate. And this is on the right, the plotted result is for these after the 6th iteration, and the fidelity of the plotted drop is 0.9912 in this case. So the results were really significant and were better than what we performed on NMR. So with this, I would like to summarize my results or summarize my work. So we designed a process tomography scheme in the context of Wigner representation for unknown quantum propagators and implemented them experimentally on NMR QC and IBM-Q. With this, I would like to acknowledge Professor Glasser for insightful discussions and ideas, European Union's Horizon 2020 program for funding the project, and QFTA 2020 organizers, and Isa Mohali. Thank you very much, and thank you for your attention.
Thank you, Amit. We can have a couple of quick questions. The participants may raise them. So, Arvind, yeah, you may ask.
Yeah, I just want to say that it's nice to see our undergrads doing well, and Amit gave a very nice talk. Congrats, Amit.
Yeah,
thank you, sir.
He's moving to Caltech. He's already in Caltech, so just wanted to congratulate him.
Thank you, sir. Thank you very much. It's nice seeing you all.
Any other question or comment?
Can I say something?
Who is it?
Shibashish.
Yeah, Shibashish, go ahead.
So I have just one naive question. Is that, there are different methods of this process tomography, because you are doing this process tomography, right?
Mm-hmm.
You are doing this process tomography, right? By estimating. So how does your method fare with the existing methods of process tomography?
So this was actually a totally different method in comparison to what we have currently. Like, we currently measure some initial states and some final states, but in this case, we are actually scanning the entire Bloch sphere for different angles, alpha and beta. So I'll show you again. I mean, sorry. Yeah, here. So We are actually scanning the entire system. So we are not we are not saying that our approach is better, but we just wanted to showcase this in the case that these drops representation and the experimental reconstruction of these drops representation is possible. And one can actually use this in the practical application as well. If you want to, if the entire scheme is very ideal and one want to quantize how much error in producing a propagator, let's say, so one can quantify using these scanning approaches. I hope this answers your question.
Okay, fine. Okay.
Yeah, if there is no other question, then let's thank Amit once again and move on to the next talk.
Thank you. Thank you very much.
Next talk is by Dr. George Thomas.
Hello.
Hello.
Yes. So shall I start?
Just wait. Yeah, you just put up title slide so that we can see that you can hear your screen.
Yes.
George, very nice to see you. And I keep saying this, that I'm very happy to see that some of our early graduates from PhD and MS are all speakers in this conference. So very nice to see that you are giving a talk.
Thank you, sir. Thank you very much. It's always a pleasure to be.
I still remember when you joined your PhD program in the early days of.
Yes.
They were amongst the first
Those
PhD
were very nice time. Yes.
First batch of 4 students.
Right.
Yes.
Okay, so maybe you can start. Our next speaker is Dr. George Thomas.
Okay.
So George is also alumnus of ISER Mohali. In fact, he has the distinction of being my first PhD student. After doing his PhD from ISER Mohali, he did his first postdoc at Institute of Mathematical Sciences in Chennai with Dr. Sivashish Ghosh. And currently, he's in the group of Jukka Pekola at Aalto University in Finland. And George is interested in quantum thermodynamics and related systems. Today, he'll be speaking on thermally pumped maser with superconducting quantum circuits. So over to you, George.
Yeah. Thank you very much, sir. And I thank all the organizers for giving this opportunity to present my work. So today I will present thermally pumped maser with superconducting quantum circuit. So the presentation will be based on this paper, basically. So first I will introduce a thermally pumped thermal 3-level maser as a heat engine. Then I will introduce motivation and some introduction about behind our work. And then finally, I will discuss the thermally pumped maser in superconducting quantum circuits. And then there are some intriguing relation between population inversion and heat power. And this we can use to detect population inversion just measuring the heat power. So that also I will discuss in the end. And then finally, I will summarize. So maser as a heat engine. So in a seminal paper by Scoville and Du Bois in 1959, they introduced maser as a heat engine. So what they did is there is a 3-level system and it is coupled to 2 heat baths, T1 and T2. And T1 is a hot bath and T2 is a cold bath. And we know that heat will flow from hot to cold. And here it flows from hot to cold via this 3-level system. So, but there is a filter which filter the frequency of the incoming radiation from the hot bath. So that filter only allows the frequency which is the transition frequency between 1 and 3. So what happens that the system can excite by absorbing one photon from the hot bath, and then the system goes from ground state to second excited state, the level 3, and it can emit a photon with frequency nu2 to the cold bath, and system comes to the first excited state. And from the first excited state to ground state, system relaxes and gives a photon. That is our output. Interestingly, that for Maser to happen, we need population inversion. That means in the second level should be more populated than the first level. And if we invoke this condition, we can show that the efficiency of this engine is bounded by the Carnot efficiency. So it is like an engine. And also it can work as a refrigerator. So to work as a refrigerator, what it has to do is it has to like if we pump the atom from 1 to 2 with a photon, then it can take energy from cold bath and go from 2 to 3, and then relax back from 3 to 1 by giving off a photon to hot bath. So it can work both forward and backward direction, and in one side it works as a heat engine, in another side it works as a refrigerator. And this is one of the pioneering work in quantum thermodynamics, and people have realized, people have done a lot of work in this direction, and some are, I'm just mentioned some of it. In quantum optical setup, they have proposed how can it be done, and in quantum dots they have done some work in this direction, and Professor Johal's group in Iser Mohali, they are also working on this optimal performance of such systems. So motivation behind our work is the to realize the thermally pumped Maser in superconducting quantum circuits. So here we convert heat into coherent source of radiation, because we have a heat flow from hot to cold, and we have to convert it into coherent source of radiation. And these kind of devices are helpful for heat management in quantum circuits. And another motivation is the recent experiment done in our lab. That is, what they did is they have a superconducting qubit which acts as a heat valve. So this there is a hot reservoir and a cold reservoir, and heat flows from hot to cold, but they can control the heat by applying external magnetic flux. So what is a transmon qubit? I will just explain that. So we know that LC oscillator is just a harmonic oscillator with the frequency 1 over square root of LC, where L is the inductance of the inductor and C is the capacitance of the capacitor here. Now, if you replace this inductor by a Josephson junction, then it is like a unharmonic oscillator. So unharmonic oscillator, that means the transition frequency from 0, 1 will be different from the 1, 2. And so that we can address any transition specifically. And all these experiments, which will be done in very low temperature, around 10-20 millikelvins, so they can actually initialize the system to ground state. And omega 01 frequency is written like this: square root of 8 EJ EC minus EC. So EJ is the Josephson energy, which is due to this Josephson junction, because the Cooper pairs tunnels back and forth in the this Josephson junction. That is the so there the energy associated with that is EJ, and EC is the charging energy of this island. And we know that omega 01 is this frequency, and the difference between omega 01 and omega 12 is EC. So there is the unharmonicity here is the charging energy. And the current through the Josephson junction, it is having this form, I equal to IC sine phi, where phi is the phase, Josephson phase across this Josephson junction. So we have a anharmonic oscillator, and we can use it as a qubit, but we have more levels in this anharmonic oscillator. But this 0 to 2 transition is not possible here, because if you it's like selection rule, it is only 0 1 or 1 2, or it is even possible 0 to 3, but 0 2 is not possible. Now, what is our setup? In our setup, the essential thing we need is a 3-level system with 0 to 2 transition. And we also need resonators with high quality factors, which we need to use filters. So I will explain that, because here we have earlier seen that we need filters to filter the spectral the bath spectrum. So the filters we use is the resonators, which is like a LC oscillator, so which has a specific frequency. So we filter this bath spectrum using these resonators, but the resonators should have high quality factors, because the resonators have a bandwidth, and then if the quality factor is very, very low, then we cannot couple this resistor with this Q-trit in a specific manner. It will couple with other unintended transitions also. So this is the schematic diagram, but I will explain how we can do it in the circuit. So there are two resistors, RH and RC. RH is the hot resistor. So it's a normal metal resistor, and these normal metal resistors is our heat bath. So we can control it by Joule heating, and we can find the temperature of it, and it's a well-defined heat bath. And this heat bath, for example, RH, is coupled to a resonator with frequency omega h. Basically, you can consider it as a harmonic oscillator. And this coupling is done by some capacitive coupling. And further, this omega h, this resonator with frequency omega h is coupled to this Q-trit with another capacitor. So this is the in this hand, and in the other cold side, the same thing repeats. The Q-trit, which is actually given with 3 junctions, as well as together with the island, which is done in this dotted, represented with this dotted square. And this Q-trit is coupled to cold resistor also in the same way. So and then we need to collect the output. So output is our photons coming from the maser, which is collected in this resonator with frequency omega d. And this output resonator is coupled to a transmission line, and then further this transmission line is coupled to a spectrum analyzer. Or after this CD prime, we can connect a resistor also. That scenario also I will explain. So now we'll just see how these circuit parameters are playing the role. For example, this I will consider this side, that this resistor is coupled to the resonator. So and then further to the Q treat. So this coupling, that means Q treat is coupled to the resonator and through a capacitor. So the coupling strength of the capacitor, the coupling strength is decided by this strength of the capacitance. So that is given here. So the coupling strength is proportional to the frequency of that resonator square and capacitance and this characteristic impedance of the this resonator. And there is one more term, size 02, that is the matrix element of the phase. Why matrix element of the phase? Because this resistor is coupled to this Q treat. The operator which couples the Q treat to the resistor is the phase. So the phase element, whatever transition you need to couple, so the matrix element of the phase should not be 0. And now this resonator is coupled to the resistor. So there is a loss. There is a now it becomes a lossy resonator because of this resistor. And because of that, the photons in this resonator, photons can be in this resonator, but it can decay to this resistor and dissipate there. And the decay rate is given by kappa h, where this kappa is proportional to this capacitance square and the resistor which we attach in the end, and also the characteristic impedance of this resonator. So we can actually control this. So we can, in lab, they can make how much resistance you need, how much capacitance you need, all these things one can make. Now, how this environment invokes transitions in this Q treat. So this environment invoke transition, and the transition rate is given here. It is proportional to the coupling square multiplied with this decay rate, and this delta is the detuning between the resonator frequency and the transition frequency which we are coupling here. And the transition rate will be proportional to this factor. And the quality factor of the resonator is defined as this resonator frequency divided by the decay rate. So if the quality factor is very low, this will be very lossy. That means the photons cannot stay in this resonator for a long time. It will decay to the resistor. And interestingly, these parameters, quality factors, can be very easily controlled while they are making the sample. So this analysis which we have done for this this side, the hot environment, can be is same for the other cold as well as for the output part. Now the thing is that if you make this quality factor very, very small, then this decay rate, that means this decay rate is very, very large, and you will see equilibrium number of photon distribution in this resonator. So we can consider then this resonator together with the resistor as part of the environment of this Q treat. But if the decay rate is not so low, or the quality factor is very high, then we cannot consider this resonator as part of this environment, but we have to consider resonator, this resonator together with the resistor.
Yeah.
So in next few slides, what I do is I consider this hot environment is, or the hot resonator is very lossy, or the decay rate is very high. So we can consider it is part of the environment. And here, this also we can consider it as the part of the environment, the cold part. And in one case, we consider this decay rate of this output as part of environment. I mean, output resonator as part of environment. But in another case, we take along with the system and we evolve it together. That I will explain. So how good the quality factors of the resonator should be. So the quality factor is given like this, and we need, so the bandwidth should be such a way that it should not invoke any unintended transitions. So which the condition follows here, this quality factor of resonator R, that means R can be H, C, or D, all the three resonator, which should follow this relation. And I mentioned earlier, these resistors are our thermal baths, acts as the thermal bath, which produces some noise, and that is our thermal bath. And these thermal baths can be, the temperature of the thermal baths can be controlled and very precisely measured using some technique called NIS thermometry, which is explained in this paper very clearly. Now we'll go back to the Q-treat. As we have seen that like in transmon, this 0 to 2 transition is not possible, but we need to have this 0 to 2 transition for the mazing purpose. Now what we did is we arrange this Josephson junction in an asymmetric way such that we have an asymmetric potential now. As we can see in the left side, asymmetric potential. And this, because of this asymmetry in the potential, now we can have 0 to 2 transition possible. Or we can say the matrix element of this psi. So this is like the psi is analogous to the position operator for a harmonic oscillator. So this the potential is with respect to psi is plotted here, and we have a asymmetry in the potential, and which in turn give rise to all transitions. Like it can have many different transitions, which is forbidden in the case of a symmetric potential. And we also need unharmonicity to distinguish between the transitions. So we have seen earlier that omega 01 and omega 12 are different. But here, because of this asymmetric potential, we can have extra benefit of this unharmonicity. Why I'll explain that when this third level, when it goes to this double well kind of structure, close to that, it will shift downward. So we can have more unharmonicity in this setup. So if we analyze this further, so we have this potential of this form. The potential is given. This EJ is the Josephson energy of any of these junction, and all these junctions are identical. And this psi x is the phase shift due to the external flux. So we can apply this external flux, and we can change the energy level of our Q-treat. Now, expanding this this potential in the minimum, we get an adding to the kinetic energy part. This kinetic energy part is this one. This 4 EC dou square by dou psi square is the kinetic energy part, and this I expanded this U up to the quartic order here. Now, if we consider the first term, kinetic energy part, and together with up to the quadratic order, then it is like a harmonic oscillator. So we get a harmonic oscillator from the first and the second term. But now we have a cubic term and a quartic term. And this, from the first order perturbation, we do not get any change in the eigenenergy due to this cubic term, but we get change the eigenenergies from the quartic term. So initially what I have shown for the transmon qubit, that comes from this quartic non-linearity term. Now, but these eigenstates can be changed due to this cubic term, and that is why we get this that's why how we get this 0 to 2 transitions. Now so as we have seen here, we consider this cubic and quartic term as the perturbation, and then we find the eigenenergies, then we get these extra terms, and then the harmonic oscillator, and now we can find the all the transition frequencies. And all these transition frequencies are different, so we can address each transition frequency separately. Now the matrix element. So we have seen that this the psi, the Josephson phase, which is the operator which couples to the environment. So the matrix element of this psi decide whether the transition is possible or not. So the first term is the nearest neighbor transition. So that nearest neighbor transition is given like here, and as we can see, for harmonic oscillator is just proportional to square root of n, that is there, but because of this extra non-linearity, we get some other terms also. And interestingly, we have now 0 to 2 transition. So 0 to 2 transition is coming from this cubic non-linearity term, and that is also depends upon the flux. So for zero flux, there is no term, but for a finite flux, there can be 0 to 2 transition. So we have to make the system and then keep it. We need an external non-zero flux to invoke this transition. And similarly, we can have 0 to 3 transition. So all these transitions are now possible. Now, once we have these transitions, then we can have this transition rate. So how this environment invoke transitions in the qubit. So which is proportional to this matrix element that we have explained here, and these frequencies, and this is the real part of the 1 over impedance. So if this Zj is the impedance of the environment, and this constitute the resonator, resistor, everything, the capacitors, everything, and the impedance, the total impedance of that is Zj, and this Nj is the Bose function. Now, this is just a preliminary experimental data based on our newly prepared sample. So we can see all the transition. We were able to fit these transitions also. So for example, here it is not very visible, but it is 0-1 transition is here, and 0-2 transition is here, and these dotted lines are the fitting. And we see all the transitions in the experiment. Now we can have a semi-classical approach of this. So once we know the transition rates, we know that this Q-treat is there are three environments, like one from the hot, cold, and this output part. So once we know the transition rates by each of these environment, then we can find the how the occupational properties of the Q-treat evolves. So that is given in here, and where this gamma is the rate matrix. And now these gammas in turn depends upon the number of photons in the resonators. For example, I put 0, 1, gamma 0, 1 is proportional to this part which we have discussed earlier, this transition rate, characteristic transition rate, and also the number of photons in this resonator. So and the transition from gamma 0, 1, that is going from 0 level to 1 level, is proportional to gamma d and d. So similarly, we have all other transition from the other environments also. So now together with these equations, we can find the steady state. Steady state means we should have the probabilities, the p dot is 0. So from that steady state, we can estimate what are the number of photons in this each resonator. So this steady state this the rate matrix, the eigenvector with which has corresponding to 0 eigenvalue, that will be the solution for this, and we can find all the photon numbers. So once we have photon numbers, we can find the power output. So we know now, for example, here how much photon here, how much photon is in this resonator, how much photon in this resonator. So once we have these things, then we know how much power is we obtain. So that is just depend upon this number of photons multiplied with the decay rate, how much it decay from the resonator to the resistor. So for a very large photon output in the output resonator, that is here. So that is what we need for a laser. So then we have this kind of simple expression, and the power input is the heat intaken from this hot resistor. So that is here, and this efficiency of the maser is power output by power input, and that is bounded by the Carnot efficiency we can show. Now lacing threshold, like we can find the lacing threshold. What is the condition for lacing to happen? That we can get from here, and here if you see that the left hand side is less than 1, and from this condition, so NH, NC, all these things are the number of photons in the each corresponding resonators. Now once we have this condition, we can get some idea how to prepare the sample. For example, we need to have these circuit parameters, that is resistances, capacitances, resonator frequency, such a way that this the decay rate of the output resonator is the smallest, and in it should be in this order, where gamma d is the transition rate of invoked by this output part on to the Q-treat. Similarly, so this is a good thing, like how we should prepare the sample. We can get some idea from here. Now we go to a quantum approach. So in quantum approach, so actually we have what? We have Q-treat and 3 resonators. So we write the Hamiltonian for the Q-treat and all the 3 resonators and their couplings. So it's like a Rabi coupling or James Cumming kind of coupling. So we have this coupling strength we have, and then uh, we have the total Hamiltonian. But as I said, that if the resonators are very lossy, then we can consider these as a part of the environment. So for example, we consider here this hot and cold as part of environment. So then we get this this Hamiltonian. Only we consider the Q-treat and the output resonator, where we keep the major output and its coupling. Now we can find the quantum master equation for it, and then we can solve this Lindblad master equation, and then we get stationary state for d rho by dt is 0. So that rho star, which gives this steady state. Once we have the steady state, then we can find the resonator state by tracing out the system degrees of freedom. And once we have this, we have the resonator state, then we can find the Wigner functions, Poisson distribution, everything we can do it. So that's what we did it here. So when the once we found the steady state and the output resonator state, so we plotted the Wigner distribution for equal to the first A and B are the Wigner function and the photon number distribution in the output resonator. So as we can see that when Tc equal to Th, Tc by Th equal to 1, we have a Boltzmann distribution for the photon number. And it is, so the dashed lines is the Boltzmann distribution, and the distribution photon number in the output resonator is the red line. So it matches very nicely. And similarly, the Wigner function is a Gaussian centered at the origin, as we expect from the thermal state. Now in the C and D, we increase this temperature gradient little bit further. So Tc by Th is 0.4. So then the Wigner function like smears out, it's like a disk now, and this photon number distribution is going towards the Poisson distribution. And we increase this thermal gradient further, then we have a photon number distribution. It's like a Poisson distribution, and the Wigner function is like a ring, which is expected from the Maser output. Now in G, we find the power. I have discussed how we get the power output. So we get this power output for two different set of circuit parameters, which is feasible to do in the real sample. So we get around 1 femtowatt power we can achieve from this kind of setup. And this is the efficiency, and which is bounded by the Carnot efficiency. That is, the slanting line is the Carnot, and the efficiency is bounded by the efficiency of the this Carnot bound. And the last part is that we have, as we know that the Q-treat is only, we have only one atom here. We have only one artificial atom here. So what happens when a photon comes, excites the Q-treat from its ground state to the second excited state, it loses one photon from the hot bath. So the entropy of that hot bath decreased like here, as I have written here. And similarly, one photon goes to the cold bath, one photon goes to the output. So entropy of this cold bath increased by this amount, h omega 12 by kBTC. Similarly, this output side, the entropy increased like this, where Td is the temperature of the output part. Now, if we have this condition that the second and third term together is positive. Suppose the second and third together is positive, then it doesn't matter that what is the temperature of TD. Irrespective of the temperature of TD, this is positive. This term is positive. So which means that irrespective of the temperature of TD, so the output part here, the heat will flow from the hot to the output. So even if this, suppose if we replace it with a resistor, for example here, if you replace with a resistor or a bath, then irrespective of the temperature of this bath, heat can flow from hot to that. And this we can understand in a different way. So if you have a population inversion in the ground and first excited state, that means it is effectively in a negative temperature, and negative temperature is greater than any positive temperature. So it should flow from the Q treat to the output. So this is a this way we can detect whether there is a population inversion or not by just observing the heat flow. So I'll just explain that. So this is the power by external flux A. So when we change the external flux, actually the energy levels are changing, and the power will of course change, and there will be a maximum somewhere where all the intended transitions meets. And now this is the population inversion. So the population in the level 1 divided by population in the ground state, which is greater than 1. That means there is population inversion. Now we keep the flux point at somewhere where we observe the maximum power output, and then just change the temperature of the output terminal. And while changing the temperature of the output terminal, we can see that heat flows in the same direction. It is not changing the direction, even if it crosses this red line. The red line corresponds to the temperature of the hot bath. So even if the output terminal has larger temperature than the hot bath, still it flows to the output terminal. And you can see in that way, in the population inversion actually decreases, but still it is there. So in this way we can, it is a kind of indirect measurement of the population inversion of the system. So to summarize, we have model a thermally pumped on-chip 3-level maser. This is made on a chip, so which can convert heat into coherent source of radiation. And then we have proposed an experimentally feasible method of detecting population inversion in the artificial atom by thermometry. Or just observing the heat flow, we can find whether there is population inversion or not. And we get all the expression of the power output in terms of the circuit parameters. So we know what are the circuit parameters, the capacitances, resistances, of the frequencies of the resonators. In terms of those parameters, we know the power output, and we can optimize further. And we show that 1 femtowatt or a few femtowatt can be achieved from the realistic typical parameters of circuit QED. And this is having much application in the circuit QED setups, and which is very good. And I thank you for your attention. I thank my collaborators of this work, Asad, Dimitri, and Yuka, and I acknowledge the funding agencies, and I thank all the organizers of this conference for giving me this opportunity. Yes, thank you.
Thank you, George. Questions? You can raise your hand if you have any question or comment.
So George.
Yeah. Yes. Yes,
sir. So this I can see that. So in order to detect the population, so
Yes.
so you are saying that even if there is the temperature of this, what is that third one called, where these frequencies omega d, so it's this
Yes.
one. Okay, so even if the temperature of this
Mm-hmm.
is higher than the temperature of the hot,
Mm-hmm.
but still heat flows, right?
Yes.
So is it not
So
so will there not be any violation of second law kind of thing?
okay. So no, because so in this equation 20, what
uh,
I have written is the kind of entropy production when
yes,
one cycle completes.
yes,
So when one photon comes from the hot resistor, and which excite the Q treat from 0 to 1, that
yes,
means that h bar omega 0 to energy is lost in the hot bath,
uh-huh.
right? So the and divided by its temperature, we that much, this the third term, that much entropy is decreased in the hot bath.
Mhm.
But there is entropy increase in the cold as well as the output.
I see. Okay, okay.
So since this TC is much lower,
Mm.
this should be positive, the total term. So actually the whole entropy is increase in the cold resistor. So the net entropy will be greater than zero.
So this condition that you have written here, the essential condition for population inversion. Okay, so
Yes.
you have a physical situation where this happens, right?
Uh,
That means this
this
condition
this
holds
this
good.
Yes, yes, yes, yes. So one thing is that we should have a uh, this. For example, I can show someone. So, for example, here we should
Uh,
have very high transition rate from 0 to 2. So it should pump very much higher, right? So it
I
should
see.
pump this Q treat from 0 to 2, and that rate should be um, and that rate is should be much higher. And similarly, this is 2 to 1 transition, that should also be higher. But
Mhm.
this 1 to 0 should be weak enough.
I see.
So that is what this condition says. Yeah, so this condition should be satisfied. And this the the output um, resonator where we collect the photons,
Uh-huh.
the decay of that resonator should be very very less. So it
I
should,
see.
the photon should go on back and forth in the resonator. It's like a mirror, it should
Mm-hmm. I see.
go back and forth for longer time.
Okay.
Yes.
Yeah, Oscar?
Hello. So very interesting talk. Thank you very much. My question is, when you do this filtering with the resistors, the result of filter function is like a Lorentzian, I guess. Is it possible to make it
Yes, yes.
asymmetric, symmetric, or maybe some nonlinear dependence on frequencies? How can we control it further? It might be interesting to reach different regions of dynamics.
Yes. So basically, yeah, this is Laurentian, but you can control this width of the Laurentian very easily, because you can control these resistors. The larger the resistor, the larger will be the dissipation. But in principle, you can change that this to asymmetry, some Fanon resonance or something. But it's yeah, it is possible. It is possible, but not very easy. But it is possible, I think.
I see. Thank you.
Thank you.
Okay, since it's about time for the next session, so we close this session by thanking all the speakers, uh, and bye-bye to all.
Thank you.
Great. So we're in the home stretch, and as Ramandeep mentioned, we are running out of time. So let me begin. The final session of QFTA 2020 has two talks scheduled. Let me introduce the first speaker, Professor Sibashish Ghosh. He's a professor in the Institute of Mathematical Sciences, Chennai, working in quantum foundations and quantum information theory. He obtained his PhD in 2001 from the Indian Statistical Institute, Kolkata. And thereafter, he's done several postdocs. He was a visiting researcher at the University of California, Los Angeles, an NBHM postdoctoral fellow in PAMU, a postdoctoral fellow at IMSC Chennai, and then a postdoc at the group of Professor Samuel Brownstein, University of York. And then he's joined IMSC Chennai as a faculty member in July 2006. His research areas are very broad: quantum information and computation, foundations of quantum mechanics, dynamics of open quantum systems, quantum optics, and quantum thermodynamics. Today, he'll be talking about quantum precision thermometry with weak measurements. So, Subhashish, over to you. It's a 30-minute talk and 10-minute for questions.
Can you hear me?
Yes, yes, but your video is not switched on. Is
okay, just a minute. Let me see whether, can you see me now?
We can hear you, but can't see you. But that's
anyway,
okay.
Can you see my
yes,
slides?
Yeah, we can see your slides.
Okay, fine.
Yeah.
Okay then. So this is work which I have done in collaboration with Arun Pati and his student Chiranjeev Mukhopadhyay, and his former student and my former PhD student Shagnik Chakraborty. Okay. So the so the idea is here that I would like to use basically the quantum weak measurement, which is a specific topic in the measurement theory, to do something to measure temperature quite precisely. And I would like to see whether weak measurement can help us to have a precision. Okay. So let me try to motivate you. So, dealing with preparation, manipulation, and detection of microscopic systems, which is being operated in the quantum regime, it requires a very high level of precision because we are dealing with microscopic system. Now, such precision, it requires very high level of accuracies in the measurement scheme to monitor and control the corresponding quantum system. So, for example, in atomic gases, it can be cooled down to a lowest temperature in the universe, even below the nanokelvin regime, and which demands measurement scheme capable of high precision at very low temperature. Okay, so moreover, the quantum system themselves can be used as probes. Okay, just like a thermometer, you can use a quantum thermometer to probe the temperature of your system and to attain an astonishing resolution in the estimation of parameters. So, for example, the most precise atomic clock which is available today is capable of measuring the estimated age of the universe with an error which is less than 100 microseconds. Okay? So therefore, it is essential to study quantum bounds on measurement precision in order to have accurate knowledge or almost accurate knowledge about such parameters as well as fundamental constants also. So as I said earlier, we are interested here to have a precision measurement of temperature using the notion of weak measurement. Okay, so this is my outline. Okay, so let me first mention to you what are our results. So we show basically a presence of optimal temperature window for which precision offered by our scheme which is also reflected in the standard quantum Fisher information based scheme. So we have basically a temperature window in which the temperature can be measured more or less precisely. And what is the crucial advantage of our scheme, this weak measurement based scheme, over the standard quantum Fisher information based scheme, is that we can shift this optimal temperature window, okay, based on the parameters which is used for the post selection in the weak measure. And also, because we are dealing with the weak measurement scheme where you need very weak interaction with the measuring apparatus and also very short time, therefore our scheme has the ability to estimate even high temperatures to some extent. Okay? And this is important because if I want to, for example, measure temperature of sun, if you use normal thermometer, of course it will not work at that high temperature. So the advantage of this weak measurement based scheme is that interaction is small, measurement interaction, as well as the time which is needed for measurement interaction is also quite small, and therefore the scope of damaging in the measuring apparatus is quite small. Right. So given this, so let me outline our, so I'll talk briefly about the scheme of weak measurement and weak values, and then I'll talk about measuring temperature using these weak values, and then I'll talk about the precision of your temperature measurement scheme using weak values, in the sense that what happens if there are some noise, then how precise our measurement, the temperature measurement is. And then I'll compare a little bit with the weak, the scheme with this quantum Fisher information based scheme, and then summarize our result. Okay. So these weak measurement, as you know, it was introduced by Yakir Aharonov and his collaborators in 1988, in which basically you have a pointer which is prepared in some initial state, PIN, and the quantum system which you are going to measure, it is pre-selected in some state rho s. So rho s can be arbitrary state of your system, yes. And the joint system pointer, okay, state, basically this tensor product state, rho s tensor product P in, and it is then evolved through some weak interaction Hamiltonian. So this is the system Hamiltonian H, tensor product, the momentum operator of the measuring apparatus, multiplied by this coupling constant G, which is very small. And for our discussion, we can take this, time is to be quite small, or G times the time to be quite small, whatever be the case. Okay, right. So for projective measurement, so this is the first part is your pre-selected state, then this weak interaction between system and measuring apparatus, and then post-selection. So this post-selection is the strong measurement. Basically, is a projective measure. So what you do, you post-select your system, okay, in this orthonormal basis UK, and as a result of that, if kth outcome comes in the post-selection, then the state of your measuring apparatus will collapse into this one, what I have written, PF, which is the final state, kth, due to the kth outcome. Okay, so this is the collapse state of your measuring apparatus, and here this quantity HK of rho, this H rho of K, this is what is known as the weak value. So which is nothing but your trace of H rho with respect to the projector of UK divided by the average value of rho. Rho is your rho S with respect to UK. So this is what is known as the weak value. And as you can see, this weak value is not a real number in general. It can be a complex number. In fact, it can go far beyond the spectrum of your system Hamiltonian H, even if it is real. Okay, so how does one, so because weak value is in general complex, how does one measure that? So there are different ways of measuring weak values. Okay, so how does one do that? Is basically you compare the initial state of the measuring apparatus with its final state. Okay, so what you do is you perform measurement on the measuring apparatus, its momentum and position shifts. So here is which was given by Richard Josa in 2007. So what you do is you take the average value of position with respect to the final state of measuring apparatus, so which has this form which I have written here, and similarly the average value of the momentum of the measuring apparatus with respect to the final state of the measuring apparatus. Okay, so once you do that, then yeah, so these are the quantities which you have to define. Mass of the pointer, T0 is the instant of end of measurement interaction, etc. Okay, so this is one of the ways of measuring the, so you basically you calculate the weak, the real and imaginary parts of the weak values. There are other ways of doing that. So for example, real and imaginary parts of the weak value has been detected using the Lagrange-Gaussian modes of the pointer states. And recently, Arunpati Ulbosisina and their students, they have also proposed a theoretical work as well as it has been verified experimentally of inferring the weak values using interference, visibility, and phase. So for detailed discussion about weak values, you can see this reference, this review article by Dressel et al. And reviews of modern physics. Okay, so that is a little discussion about the weak values. Now let us use these weak values for measuring the temperature. So let us consider your system to be d-dimensional, and it is under the action of some time-independent Hamiltonian H having non-degenerate energy eigenvalues E1, E2, Ed with corresponding eigenstates, energy eigenstates psi1, psi2, psi3, etc. And let us assume that this system is in contact with a heat bath at temperature, and let's also assume that the system has acquired the equilibrium temperature. Okay, so therefore the state of your system will be basically this rho t, which is the the canonical ensemble state of the system. So beta is one of, so inverse of temperature, and I have taken kb to be equal to 1. Okay, so what I do is I take the measuring apparatus initial state to be a pure state. So P in is basically projection on a pure state with its position wave function phi of x. So what we would like to do is we would like to perform measurement of an observable A of the system in the weak measurement setup under this action of this, this interaction Hamiltonian on this initial state rho t tensor product P in for some time tau. Okay. So the question is, so the basic assumption is that during this interval of interaction 0 to tau, the system and measuring apparatus, they are under the action of only this interaction Hamiltonian. Nothing else is working. Okay. So there are ways of realizing it. One possible way is that you assume that the system S has acquired the equilibrium temperature, and then you take out the system from the bath, and then you interact with the measuring apparatus. Other way out should be that the strength G of the interaction is much higher than that of the system Hamiltonian during the small time interval 0 to tau. So therefore, change in the states of the system happen only under the interaction Hamiltonian. Okay, so under this interaction Hamiltonian, the joint state, time evolved state of a system and measuring apparatus will be rho Sm tau, which is of this form. And because I have chosen this G tau to be very, very small, because we are dealing with weak interaction, so basically this is the state rho t tensor product phi minus Ig tau of commutator of these two operators to the first order in G tau. Okay. Now what we do is we post select the system S to be in some final state, so psi f, I post selected it. Okay. So if I do that, then the unnormalized collapse state of the measuring apparatus, it will become like this. So approximately it will be of this form. So basically the average value of the the Gibbs state rho t system state times this eta of tau. Eta of tau is a normalized state, and the theta of tau has this form. So this is basically a pure state, right? So here you see that this AW is the weak value. So here this weak value is appearing. Okay, so basically our idea is by using this weak value, which I told you how to measure it, and the prior knowledge of your post-selected state psi f, prior knowledge of your observable A, and the energy spectrum of the Hamiltonian, one can in principle find out the value of this temperature of the group or of the bar. And one important thing with weak values is that this observable A of the system must not commute with the Hamiltonian, system Hamiltonian. Why? Because then this weak value AW will not contain any information about the temperature. Okay, good. So let us talk about this high temperature limit. I told you initially that there is a chance of using this weak value and weak measurement scheme to estimate high temperature. So let us talk about high temperatures. Let's say this observable A has eigenvectors Aj with corresponding eigenvalues small h. So AW, one can see it has this form anyway. And for the high temperature limit, so beta is 1 upon so inverse temperature. So therefore, to the first order in beta, e to the power minus beta will be 1 minus beta. And therefore, using this, one can find out that the weak value will have this form. So basically, the 0th order term is nothing but the average value of A with respect to the final state psi f plus beta times this one. Okay? Right. So one can invert this relation and figure out for high temperature, that means low value of beta, you have this expression for this beta, approximate. Okay. So now what you can do is, so to have a concrete expression for this beta in the high temperature limit. So let's take this this so-called Weidmann's formula. So this formula tells you that if you take any observable A and any state psi, then of course I can write the effect action of A on psi in this form. So basically this is the linear superposition of psi and its orthogonal state psi tilde. Okay, right? And then you can, so Weidmann's formula tells you that what will be the value of A and what will be the value of B. So basically A is nothing but the average value of this observable A with respect to psi, and this B is nothing but the this delta of A with respect to psi. So this is what is known as Weidmann formula. Okay, so using this Weidmann formula, you can write down the weak value in this form. Okay, so weak AW is basically the average value of A plus this the dispersion in A with respect to psi times this quantity. Okay, and therefore the beta, which is the approximate value of the inverse of temperature for high temperature limit, will have this form. Right. Anyway, so this is what we have. So as I told you, so this is a schematic. Let's say this is my measuring apparatus M, okay, and this is interacting with the bar, which consists of say qubits. So it is interacting. So once these qubits attain this temperature T, therefore the apparatus is basically interacting with one of these qubits. Right. So this is the schematic. Okay. So now let us talk about the high temperature limit, but with a specific system, namely a two-level system, two-level quantum system. So in this case, because for a two-level system, I told you psi f tilde is orthogonal to psi, and similarly psi f double tilde, which is basically the psi f tilde corresponds to the observable A, psi f double tilde corresponds to the density matrix rho T, and because you are dealing with two-level system, they should be same, psi f tilde and psi f double tilde, and therefore beta will have this form. Okay, so in weak value and weak measurement scheme, there is something called anomalous weak value. So as I said, the weak value can go far beyond the spectrum of your Hamiltonian. So the question is, if I look at the real value of the weak value, how far is it from the actual average value of your observable? So which is known as this delta A, which is known as the anomalous weak value. And you can find out its expression in terms of this covariance of A and rho t divided by average value of rho t. Okay. And you can take this inequality, and this will give you basically a lower bound on the temperature that you want to measure, you want to estimate. So in this expression, you see that this lower bound, if this anomalous weak value is very high, which is always possible, which is not impossible, which is possible, then you see that this T has a lower bound, which is basically the average value of the Hamiltonian, system Hamiltonian with respect to the post-selected states. Right. So this is about the high temperature limit in the two-level system case. Okay. Now, what about two-level system measuring the temperature using weak values, but arbitrary temperature? So let us take your system Hamiltonian. This is the spectral decomposition. So E1 with energy eigenvectors psi1, eigenvalue E1. And oh, sorry, there is a typo. It should be E2 psi2 psi2. Okay, so E1 and E2 are the energy eigenvalues of this two-level Hamiltonian, and corresponding eigenstates are psi1 and psi2. Sorry for this. Okay, so now you choose this observable A, which is nothing but your your sigma y in this basis psi1 psi2, and psi f is basically the plus one eigenstate of sigma x. Okay. So if you do that, then you can figure out that the weak value AW will have this particular form, I times this fraction. Okay. And you can figure out that for high temperature case, the inverse of this temperature beta, which is quite small, which has approximately this value, minus 2IAW divided by the energy difference. So you see that by as I told you, there are several ways of calculating the weak value. So if you calculate the weak value, because you know what is E2 and what is E1, you will figure out an estimate of inverse of temperature, and therefore the temperature also. This is in the two-level system. Okay, so that was about using weak value to estimate temperature, and in particular high temperature, and I specifically talked about a two-level system. Let me discuss about the precision of the scheme, of this temperature measurement scheme for a two-level system. I'll only concentrate on two-level system. So there are two ways to talk about this precision. One is that I told you that our probe has attained a equilibrium temperature. Let's say it has not yet attained the equilibrium temperature. It is, say, some sort of non-equilibrium case, close to equilibrium situation. And the other one is I'll have to do this post-selection, and let's assume that the post-selection is not accurate. It has some noise also. Okay. So I'll talk about these two things separately. So first I'll talk about what happens if the thermalization is imperfect. So you can assume, for example, that the probe has not yet reached the equilibrium temperature state, the Gibbs state rho t, but it has a little bit of noise. Okay? Right. So rho t delta. So this is the delta is the amount of noise which is with a projection on a pure state, let's say, where the chi of theta phi can be random. Okay. So if I take this one, and I told you how to calculate these weak values AW, one can figure out that for the inverse temperature, beta, which I called as beta tilde, it has of this form, 2 times tan hyperbolic inverse of this quantity divided by E2 minus E1. And now, if I take quatermative expansion of this weak value with respect to delta equal to 0, and keeping terms up to first order in delta, you can figure out that this inverse temperature beta tilde has this form. Okay, where C1 and C2. So this capital delta is the difference, energy difference, E2 minus E1. And C1 and C2 has this form. Okay, so you can see that C1 and C2 are both functions of the Bloch sphere angles theta and phi. So here we will talk about specific error, unlike in the quantum Fisher information based scheme. So we will talk about what is known as squared relative error. So what is that? So beta tilde, this is not the actual value of the inverse temperature. The actual value is beta. So you take the difference square and divide it by the original temperature square, beta square, and then scale it by delta square. So because delta is the amount of noise, so scale it by delta square. So therefore, this mean square relative error, what you do is you'll have to average over all possible choice of theta and phi. So if you do that, then this will give you the mean square error, n beta square. Okay, so now if I take this mean square error, so it is in the case of two-level system. Again, I take this observable A to be sigma y, and my post-selected state, now I parameterize it, cos xi by 2 psi 1 plus e to the power I nu sin xi by 2 psi 2. This is the most general pure state, post-selected state. So if you do that, you can figure out that the root mean square relative error in beta has this particular form. And then, if you take special cases of these post-selected states IF, you can have this expression for the root mean square relative error. Anyway, so I'll not go into this. So basically what I want to tell you is that if you calculate the estimated inverse temperature beta in this scheme, it will give you a estimated temperature to be T to be 0.79. Well, I'm not using any unit here, but we have already mentioned what are the values like H cart, KB, etc. So this will give rise to 0.79 kind of. On the other hand, if I do this quantum Fisher information based analysis, I'll talk about it later, then the optimal qubit thermometric probes with unit energy gap, so E2 minus E1 is equal to 1, which I'll take throughout this thing, it will turn out to be 0.41. Okay. So therefore, so this I'll show you in figure 2. I'll come back to that, figure 2. Now this is for specific choice of, so this value, estimated value 0.79 is specific choice of the the post-selected state IF. If I now choose another post-selected state, I'll have another estimated temperature, and that I'll show you in the plot 3. So so which one will give you the most precise temperature? Basically, if I take the post-selected state IF to be very, very close to these initial state psi, then that will give you the best choice. But unfortunately, if I take psi f to be equal to psi, then this weak measurement scheme will not work. Okay, so this is the plot, first plot. So you see that this green line, green curve is for psi f is equal to 1 upon square root. So like square root of 1 minus epsilon psi 1 plus square root of epsilon psi 2. So epsilon I have taken 0.01. Okay, and this red curve corresponds to this equal superposition of psi 1 and psi 2. Remember, psi 1 and psi 2 are the energy eigenstates. Okay, so you see that the tip of this green curve is somewhere, I think it is 0.79, something like that. But the tip, the maxima of this red curve is slightly on the right hand side. Okay, so this is a kind of, so 1 by eta, so on the y-axis it is the inverse of this error. So this will basically tell you what is the precision of the scheme. So as you can see from here, as the temperature is close to 0, you have more and more higher and higher precision, which is also reflected in this figure. So here I have taken my state psi f to be this parameterized state, as I mentioned here, cos psi by 2 psi 1 plus e to the power I psi this thing. So here you see that the optimal temperature is in this region, this yellow curve. So this is a basically, actually it is a three-dimensional plot with nu and xi. So the optimal temperature increases on this right hand side. Okay. So this tells you that and this is, of course, it does not, this figure does not tell you anything about the precision. So this is the precision. So you see that the precision is higher precision for this range of choice of your, this yellow range of choice of your post-selected state. Okay. So this is about, so this is again the precision of, so these are two plots. For one is for the low temperature, T is equal to 0.05, and the other one is very high temperature. Okay. So you see that for low temperature, okay, the left hand side, so you have a higher precision on the left hand side of this plot, whereas here you have higher precision on the right hand side, which is basically the light shaded region here. So basically it tells you that at high temperature limit, the scheme works slightly better way, because these precisions on the left hand side is what, 1 into 10 to the power minus 7, something like that. Okay, fine. So that was the comparison with the precision and the temperature. So now let us talk about the measurements post selection. What happens if it is not precise? So let's take the post selection to be unsharp. So let's say that instead of the pure state psi f, it is the unsharp version, 1 minus epsilon psi f plus epsilon by 2 identity. So in this case, you can figure out the weak value, which I denote as AW epsilon. And then you can also figure out the inverse temperature, approximate inverse temperature. Again, you can figure out what is the squared relative error, n beta square. So you choose the observable A to be sigma y, the energy difference to be 1, and the post-selected state psi f to be of this parameterized form. So if you do that, you will see that this is again, so this is the precision. As you increase the precision, you see that with respect to temperature and xi. So here I must say that in this scheme, this angle nu doesn't play much role. So you see that in this region, yellow region, you have a higher precision for measuring the temperature. Okay. So
Shibashish, I think your slide
yes,
is frozen.
Frozen. Oh,
Yeah,
shall
now
I
it's
again?
fine. No, now it's
Now
fine.
it's fine.
Now it's fine.
Okay. Okay, so now here this is a comparison between the optimal temperature and the precision. Okay, so the left hand side is the optimal temperature I have plotted. Okay, so on the left hand side plot, on the vertical axis is the optimal temperature, and horizontal axis xi by pi. And the right hand side I have plotted the precision on the vertical axis, and horizontal again xi by pi. Okay, so you see that your optimal temperature, it increases, okay, from some value like 0.54 to some value here near like 1.1 or something, but at the same time your precision decreases, so something like this. And note that here this error in beta does not have any dependence on the angle phi. Okay, and this optimal temperature has also no dependence on this angle phi. So phi is, remember the post-selected state, I have chosen psi f to be cos xi by 2 psi 1 plus e to the power I phi sin xi by 2 psi 2. So neither n beta nor t optimal has dependence on phi. Okay, so you see in this particular case that your precision, optimal temperature increases but your precision decreases. Right. So you'll have to be careful to have this window for the optimal window for measuring the temperature precisely. Okay, so let me discuss a little bit about this quantum Fisher information based weak thermometry and how does it fare with our scheme. So as I said, so far we have looked with the robustness of the precision of weak measurements based scheme. So let me talk little bit talk about the the QFI based scheme. So QFI based scheme, that for example, if it is a one parameter estimation, so you look at the fluctuation of the delta U of this parameter U. In our case, it is basically the temperature, and this is so this a lower bound on this fluctuation is given by what is known as quantum Cramer bound. So delta U is greater than equal to 1 upon square root of n times f of u of rho u. And this f of u rho u is basically trace of u times the square of the symmetric logarithmic derivative LU, and this is what is known as quantum Fisher information in the state rule. So this LU is your symmetric logarithmic derivative. Okay. So we know that this limit, this bound is achievable in the quantum limit. Okay, fine. I mean, in the achievable in the sense that you can design a measurement scheme by which you can achieve this value of delta U.
Shibashish, sorry
Yes.
to interrupt, but you just have a few minutes to wrap up.
Yeah,
So
sure.
that
Maybe 2-3 minutes. Yes.
sure.
Okay. So for pure state case, I'm not giving you the explicit expression for the Fisher information, but for pure state case psi u, you have this expression for fu, which is the expression for the Fisher information, and in our case, the post-selected state m after the system is being post-selected basically in psi f is this one. Psi of t, basically psi of u, is this pure state. Action of this operator on this phi. So phi is initial state of the measuring apparatus. Okay, so you can calculate what is your Fisher information in this case, and to the leading order in g of tau, g times tau, you can find out that square root of this Fisher information will be of this form. So I have taken not exactly the square root, some quantity proportional to it, which I have called f of tilde. So this is the scaled, precision, you can say, is f tilde. Okay, so for qubit case, you can again figure out for this choice of a to be sigma y and psi f to be of this form, you can figure out what is the precision and what will be the temperature. So now I have plotted here the scale precision, this f tilde with respect to tilde, and I have chosen this phi to be 0, and this is the energy gap. For different values of theta, you can, so this is for theta is equal to 3 pi by 4, etc. So you see that for theta is equal to 3 pi by 4, you have a larger precision, whereas for theta is equal to pi by 2 or pi by 4, this is a very low precision. And the important thing is, by looking at this plot, you can see that if I change the post-selected state, that means if I change the theta, the precision is dropping sharply, unlike in the case of this weak measurement, I mean the scheme which we described earlier. Okay, so this is what we mentioned. So let me discuss, let me conclude. So what we have done is we have presented a scheme for measuring temperature of a quantum mechanical bath through measuring weak values of on a probe, okay, which is thermal equilibrium with the bath. And the scheme relies on careful choice of the Hamiltonian generating the weak interaction and the basis of the post-selection, okay, so that you can find out what is the optimal precision window for temperature. So our scheme, of course, is applicable to any dimension, although we have concentrated our scheme for 2 dimension here. And it is important to see that there is a narrow window of temperature in which you have very high precision, similar to what is you get to see in quantum Fisher information based scheme. But the important thing is you can shift this window by changing the post-selected state. So there are a couple of open questions. So comprehensive description of the scheme for higher dimension is that which we have not done yet. And in particular, whether the location of the operating window for precise measurement of temperature can be made more tunable with higher dimensional probe. So that is what one should look at. So to figure out the form of the optimal energy spectrum of the probe in the case of arbitrary dimension, and to check whether the corresponding Hamiltonian is experimentally feasible one, that is what something we would like to look at. So this weak measurement based thermometry, it is useful estimating high temperature, as I mentioned, because the interaction time and the interaction strain both are small. So in particular, this is a wild case whether the scheme can be used for probing the temperature of the core of sun by using the probes as the solar neutrinos. Thank you very much for your attention.
Thank you, Shibashish, for a very nice talk. The floor is now open for questions. Please raise your hand and we'll get to you. I think we'll have to give people, there was a, yeah, I can see Thomas. Could you please unmute yourself? There's a question by Thomas.
Yeah. Hello, Subhashish.
Hi, how are you?
Good to hear your talk. Thank you very much. Very interesting. I just want to understand better your choice of weak measurements. So I understood that you know that you have a small interaction period, and you have a weak coupling, and but you know you could of course just do an unsharp measurement of the energy. You would also get some temperature dependence. So what is the advantage of taking the weak value?
Okay, so the question is, as I said, that you know, I have shown here some of the, so one particular thing is that because this weak measurement, you know, it requires this weak interaction as well as the time of interaction is very small, right? So therefore, you know, in particular, if I want to probe very high temperature, for example, now you might say that, look, you don't need so much precision for measuring high temperature. Okay. So that may be the case. But let's say I need precision for even for measuring high temperature. In that case, you know, the probing system will have basically, or the measuring system will have a very, very short interaction, a short time interaction and weak interaction with your bath. Okay. And this will basically result, so therefore it will not hamper the measuring apparatus, so that the measuring apparatus can work to some extent properly. So that is one argument. The other argument is that, you know, in weak values, we have the weak value, you know, it can go far beyond your spectrum, right? Energies, I mean the spectrum of your observation. Sure. And that will sometimes help you to have more precision in the parameter that you would like to estimate. So these are basically the two reasons. There might be some other reasons also.
I see. And then you also, may I just say, you also mentioned that there is a dependence of the regime of the temperature, where the precision depends on what the final state is that you post-select. So you can basically shift your focus to a certain thing, and that you probably couldn't do if you just did a weak measurement, but without a weak value. You know what I mean?
Exactly.
Yeah.
Exactly.
Correct.
Yes.
Okay, I understand. Thank you. Cheers.
Yeah.
Speak to you later.
Arvind, can you unmute yourself?
Yeah. So, Subhashish, thanks for a detailed talk. See, what I want to understand is when you talk about damaging the apparatus.
Yes.
I mean, I will send a probe, and then apparatus will interact with the probe. So even if the temperature of the object I am measuring is very high, probe will only bring a little bit of energy from the source. So why are you so much worried about damaging the apparatus?
Yeah, so of course, it's a relative thing. So what is the energy of your probe? That is of course important here. Okay. So I have taken, of course, a two-level system, so energy may not be very high, etc. But in case you have a probe which is having very high energy, then of course it will damage, right? High energy and high temperature also. So it is not necessary that your probe should be always a tiny one, right?
Yeah, so which means if you don't want your apparatus to be damaged, choose the right probe. That's all what you need to do.
Exactly. So that is why I said
probe does not bring too much energy.
Exactly. So that is why I said in the end.
I mean, once you choose your.
Yes. Yeah, please carry on. Yeah.
Go ahead. Yeah.
No, please tell me.
No, go ahead. I'm listening.
Yeah. So basically, that is why I said in the end that maybe the scheme, I don't know, it's a wild guess. Maybe it can be used, for example, to estimate the temperature of a very hot object like core of sun by using these probes, which are, of course, we know that they don't hardly interact with anybody, like this neutrino, solar neutrinos. Okay. So, of course, the emphasis is not well, I said for motivation, but emphasis should not be on the high temperature of the probe so that it can damage. No, the emphasis should not be there. But this is just to motivate.
Okay. Okay, I don't see any more questions, but you can always type them in the chat box, and I'm sure Shibashish will get around to them. So I thank Shibashish for accepting our invitation and giving such a nice talk. We now move on to the last talk of this session, the last talk of the conference. That is by Professor Jan Buda. He's an associate professor of Masaryk University, Brno, Czech Republic. I hope I pronounced everything properly, and he heads the quantum information group there. Jan has extensively worked in quantum cryptography and key distribution, and today he will be speaking about private quantum channels for multi-photon pulses and unitary K designs. So Jan, over to you.
Okay, thank you, Kavita. Let me
I just want to say hello to Jan, and also want to say that the whole world is coming in the way of our meeting, because I was supposed to visit Jan, and then the lockdown came, and then when he was supposed to come and give a talk here, then lockdown continued. So we shall definitely meet, Jan.
Yeah, thanks a lot, Arvind. I was just about to mention it, that first of all, I would like to thank you for the online invitation. And second, I hope that one day either me or you will physically, that either I physically arrive to Mohali or you physically arrive to Brno again. So let's hope that we will survive this. And let's go straight to my talk. Sorry, it seems there is something with my voice, but let's hope it will get better and not worse during the talk. So my lecture is about private quantum channel for multi-photon pulses and their relation to unitary design. It's a joint work with Mario Zeman and Misha Sedlák from Bratislava. And you can find the paper on the archive if you want to take a look at the more technical details. Okay, since I guess there is quite wide number of people with different backgrounds following this talk, I will start with introduction of what it try to motivate the problem as good as possible. So what is the encryption problem? Is the standard situation I'm sure many of you have encountered already. So for instance, when you are in a school and we are passing around the class a letter and you wanted to make the message not intelligible to other students, what you did, you used some kind of secret writing. By the way, that might be a useful comment. Do you know that the oldest mentioning of the cryptography or encryption in the world is Kama Sutra? And it's quite interesting, and I just discovered it by an accident, because my supervisor Vardo Buzek we were discussing whether I can put only a scientific literature in the references of my PhD thesis many years ago. And he told me, if it's relevant, you can put there Kama Sutra. And I checked the Kama Sutra, and actually it seems it's really the oldest reference in the world to encryption. Okay, so let's go back to what is encryption. So basically you have some text that you want to send to other participant. Usually in cryptography, it's called plain text. And somehow you want to transform the plain text into a different message that is called ciphertext. Then this message is transmitted via some public channel. It can be either internet, or it can be this secret letter that you are passing over in your class. Then you somehow want to decrypt it, and then you are able to read the plain text. In order to do that, of course, the two partners that have to encrypt and decrypt the information, they're sharing some secret in advance. They must have some advantage over the other participants who are trying to listen to the message. And this advantage is usually called the cryptographic key. You can think of it usually as a random bit string that is random. It's secret and only known to these two participants. So what usually happens is you are sharing these secret number. And this secret number allows you to choose an encryption and decryption function out of pre-agreed set of encryption and decryption functions. So what happens, you get a plain text, you apply the function, then you transmit some other bit string, then you apply the decryption function, and then you get the plain text again. Not to lose the time, I will not be giving you the classical definition of the perfect secrecy that was introduced by Claude Shannon, but I will try to move straight forward to the quantum case. But first of all, slightly modified scheme. So typical implementation of the encryption text, you take some function f, and the decryption function will be just the inverse function of this. Maybe very well known absolutely secure encryption system is the one-time pad, and the one-time pad has the plain text is only a single bit, the ciphertext is a single bit only, and there are only two possible encryption functions, the identity and the not operation. So basically, that's the one-time pad. Now let's take a look at the quantum example. What are we going to do if we want to encrypt quantum state? So basically, you start with some plain text. I'm mentioning here explicitly photon because if we are going to discuss or consider quantum communication, then typically the candidate system to transmit the information over the long distance will be photon. So you take a plain text that is somehow encoded into a state of a photon. Then you apply our encryption operation. In this particular case, it's slightly restrictive, but not as much. The possible encryption operation will be some unitary operation. So apply some unitary operation out of pre-agreed set of unitary operations. Then you are transmitting the photon that is somehow encrypted. Then you apply the inverse unitary operation, and you get the original plain text photon. Okay, and of course, for this to work, you must have some pre-agreed set of unitary operations, finite, from which you are choosing the operation based on the key. Okay, and this leads us to a definition of something what is called private quantum channel, which basically is the encryption of quantum information. It was introduced 20 years ago by Ambanis Mosca, Alan Tepp, and Ronald DeWolf. And we say that the four tuple P, U, P, rho, and so on is a private quantum channel where P is some set of plain text. Typically, it will be the whole Hilbert space of a single qubit or a number of qubits, for instance. U, this is some set of unitaries. Here you have some probability distribution on these unitaries, and the rho is some mixed state. Then we state that this four tuple is a private quantum channel if for each possible input plain text state, that's why it's called P, for each plain text, if you apply randomly one of the unitaries, then on the average, you will get the state rho 0. So what to take from this? So basically, it tells you that you have this fixed set of unitaries, fixed set of probabilities, fixed probability distribution. And whatever plain text state you take, the average output state will be the same. That's the important part. So for all plain text state, the average output is the same. What does it mean from the practical point of view? Well, of course, the adversary, he knows the specification of the encryption system, but he does not know which particular unitary was chosen. So his best strategy, if he wants to do a discrimination, for instance, is that he has to discriminate between the average states. And since the average state is the same for all possible inputs, this means that he cannot discriminate between the inputs. So this is one way to understand the security definition. Okay, so all of the average states must be the same. Just a comment, depending on the choice of the plain text, practically always, as soon as the all possible plain texts are all possible states of some Hilbert space, then by linearity, you get that the only possible candidate for row 0 will be the maximally mixed state on the Hilbert space. Okay, so this is just for generality, but basically you can think about it that it's secure as soon as the average output state is equal to the maximally mixed state. That's perfectly sufficient understanding for that. Also, this is just a side comment that we will use later. You know that the maximally mixed state, it's actually equal to the calculation when you take any state and you apply randomly according to the Haar measure distributed unitaries. Okay, we'll be using this very soon. Okay, maybe an example. So what can a typical quantum encryption system look like? So in case, sorry, in case we are talking about qubits, then the private quantum channel will be formed by these 4 operations, the Pauli operations, together with uniform distribution. And basically, you know that whatever input state you take, if you apply randomly one of the 4 Pauli operators on the out and make an average over that, on the output you will get the maximally mixed state. And
Jan, we've lost.
Sorry, can you hear me now? Hello?
Yeah, now we can hear you.
Okay, good. So once again. So we have, so in case of
so you were at the maximally mixed state.
Oh, I see. Okay, sorry. So the maximally mixed state. Okay, so practically, if the set of possible plain texts is the whole Hilbert space, regardless of what Hilbert space you have, then by linearity, the only possible state row 0 would be the maximum mixed state. So if you just forget about this and you say the maximally mixed state, it's perfectly sufficient for the understanding. And this is just a side comment that we will use very soon. Just recall, if you take any input state and you perform the average of this state on which you applied Haar random unitary, then you will get the maximally mixed state. We will use this fact soon as in one of the comments. So just an example to give you some idea what a private quantum channel may look like. A specific example is called the quantum one-time pad. It's about encryption of a single qubit. And you apply randomly one of the Pauli operators together with uniform distribution. And you know that this is the same as the quantum teleportation. So in fact, the quantum teleportation does encryption of quantum information, does the quantum one-time pad. And the 2 bits that you get out of the Bell measurement, they are the equivalent of the classical key. Okay, so if you want to do the quantum one-time pad, here you have the input plain text. You have 2 bits of the classical shared key. You apply the control sigma x and control sigma z, for instance. Here it's transmitted. This is the encryption. And here you apply, oh, sorry, it should be opposite, but whatever. It's not important. Opposite would be better. And you apply the inverse, and you get the plain text again. Okay. So this was about encryption, and let's take a look. Let's make a bit of a sidestep. So let's take a look at something what is called a unitary T design. So we have some set of unitaries. In the full definition, we have some probability distribution as well. I skipped it here, not to complicate the things unnecessarily. And we say that such a set of unitaries is a unitary T design if for all states it holds that if you make an average of a T-fold tensor product of this unitary, apply to this row, then it will be the same thing as if you make the T-fold Haar random twill. Okay, and you can see that the special example of this, when the T is equal to 1, that's the encryption, right? So the encryption, the private quantum channel I was showing you like 2 transparencies ago, it's an example of unitary one design. And I mean, these sets of unitaries, they actually have a number of applications, and they have been studied, you know, for they have been found to be very useful in a number of situations. The basic motivation is that if you look at the hard will, then you have in principle infinite number of unitaries you have to sample from. And even when you want to approximate it only, it would be very inefficient because you have to sample from a very large number of unitaries. So you are trying to find some smaller sets that do the approximation for the hard random unitary for some t. Okay. So this is unitary t design, and in particular, two facts will be useful for us. First one, if you have a unitary t design, it's automatically a unitary t minus one design. You can see it very easily. You just take the row, put there an auxiliary factored system, and you apply the definition of the t design, and you trace out one of the systems, and you will see that automatically it implies the condition for all states on the smaller system. Okay, and as a side result of this, you get, okay, just a note, and the private quantum channel is a unitary one design. Okay, now this will be quite important because let's take a look. So let's consider the following situation. If you are designing normal encryption of quantum information, you just take the input photon, you apply randomly one of the unitaries, you get a single photon, you continue, you apply the decryption operation, and you get a single photon back again. But the usual notorious problem is whether you have a single photon or not. It's quite well known to cause big troubles in QKD schemes. But maybe surprisingly, maybe not, it makes the encryption insecure as well. So what will happen if into such an encryption device, instead of one plain text, you will get 4 copies of the plain text? Because you have some laser, you apply some encoding operation, and then it enters the encryption. But instead of 1 copy, you get, say, 4 or 5 copies of the photons. What will happen? Well, of course, to start with, if you are using just one design, it would not be secure anymore. An example, just consider a very trivial example of the quantum one-time pad. Consider that you are getting a 2-photon pulse and compare the pulse that comes in the state 0, 0. It means you get state 0, 0, and you apply the same operation on both of these zeros. And then consider plus, plus, and you apply the same unitary on both of these, and you make the average, and you will see that you will get a completely different outcome states. So it means that if you have a multi-photon pulse at the input, and you are using just normal encryption of quantum information, it stops being secure. And then the solution either is to somehow force yourself to use a single photon pulses, or maybe we can do something and we can choose a different set of unitaries that will actually do the encryption even for the multi-photon pulses. Okay, so this is the multi-photon encryption that we are going to address. All right, so just to motivate, you might be already probably guessing that the answer for the multi-photon encryption will have something to do with the high random unitaries and also with the unitary T designs. But first, before we start discussing this, we have to bridge a small gap, because we are talking, on one hand side, we are talking about the photons and the multi-photon states. And at the same time, we have the unitary designs, but these are formulated for qubits. So we have to find a reformulation of the multi-photon pulses into multi-qubit states. Okay, so sorry. So we have a multi-photon pulse of polarized light, This means we will be discussing about the most general situation. So it's not a 5-photon or 6-photon, but there's a proper superposition of the photon numbers. So let's follow the following derivation. So the free electric field oscillates in the plane that is perpendicular to the direction of the propagating light wave. And basically it has two evolving components, which behave as two harmonic oscillators. And we may also introduce creation and annihilation operators, AX and AY for the two axes. And in the free space or in the isotropic optical fibers, the two oscillators are independent and simultaneous eigenstates of the number operator, which is this. Sorry, and the number operators exist. Okay, so what do we get? Now, an arbitrary normalized state of the related Hilbert space now can be expressed in the following way. So it's a superposition of M and N, and these are these X and Y photon numbers. Okay, yeah. So to give you an example, the state with no excitations, the vacuum will be this. So the single photon pure state, we can express it as a superposition of horizontal and vertical polarization. So it's alpha and beta. So it will be basically this state, okay, or alpha this, beta of this. And finally, when we come to a general N photon state, with the number of photons being equal exactly to N, we will generalize it to a superposition later. So it will be this kind of state. So this is the N photons with the same polarization specified by alpha parameters alpha and beta. So this is the state, and you can see that this N photon state, it actually belongs to N+1 dimensional Hilbert space, and we will call it Hn, and it's spanned by these vectors. Okay, now let's take a look and compare it to qubits. Sorry. So, so as I mentioned, if we have N photons with the same polarization, we are getting this state, and we compare it to a state of system of N qubits, and each of the qubit is once again prepared in the same state. And what we get is basically this. You can see it's very similar, except that this Sk, it's the totally symmetric state of N qubits that has K zeros and N minus K ones. So basically, we could have used even this notation, but we prefer to use this one, not to create a confusion. So you can see that using this, we have find some similarity, some link between the N photon states with the same polarization and between N qubit states that are made up of N qubits, all of which are in the same state. Okay, so once again, you can see these states. So we can actually define a bijective isometry between the N photon subspace and the totally symmetric subspace of the N qubit, and it's by mapping the state K and N minus K to the state Sk and vice versa. Okay. Now we have to now introduce the total Hilbert spaces to see the whole picture and not just the N photon and N qubit states. So by Kn plus, we define a totally symmetric subspace of N qubits. And just by definition, K0 will be some dimensional Hilbert space. And then this isometry gives us an isomorphism of these two Hilbert spaces, but also it induces an isomorphism between the Hilbert space H, which is the space that describes all possible N photon states. Sorry, not N photon state, multi-photon states, where each of the photons has the same polarization, and the space K, which is a direct sum of the totally symmetric spaces for n qubits, for n going from 0 to infinity. Okay. So now what we got, we managed to find an isomorphism or somehow found a translation of our language of the photons to the language of qubits that we need for our derivation. Okay, I see I have to speed up a bit. And assuming we have some polarization state psi, and we have the state of n photons that have the same polarization of psi, that we will make it, we will map it to an n-fold tensor product of the state phi. Now, we specified states. Let's see what happens with the unitary operations, because this is important for us. We would like to see if we try to do the unitary U on a single photon state, what does it do on the multi-photon state, and how does it translate to our Hilbert space, sorry, to our qubit vector space. So what we basically get, that if you have any unitary on the photon, single polarizing, it will basically induce this kind of n-fold unitary tensor product on the phi n. That's what happened. And just for the notation purposes, we'll be calling this unitary Ln of U. And now if on the input is any general multi-photon state with the states with the same polarization, then on the whole space we are getting this unitary transformation, and it's a direct sum of the unitary transformations on the respective subspaces. Okay, and also very useful will be that when we take the map that maps U of the U2 group, we map it to Ln in the space of linear operators on Kn plus, then it's an irreducible representation of the unitary Un of order n2. Okay, so we have the problem, and let's see what happens. So let's now assume, although it will be manifestly impractical, that what we actually do, that in the encryption phase, we are not sampling, we are not putting randomly one of very small unitaries, not one of one design, but we are putting randomly a unitary operator chosen according to the Haar measure. Well, so let's see what happens. Let's assume that the source is not ideal, and it prepares a multi-photon pulse for unlimited number of photons, but all of them, they have the same polarization. And now when we apply the Haar random unitary on this state, then in the qubit isomorphism, we obtain this. Okay, actually the important part is to take a look at this. And as you see, it commutes this kind of operator because it's a Haar random twiddle. It commutes with any operator from the representation LU. And by the Schur's lemma, we get that rho prime, this matrix, is blocked diagonal in the irreducible subspaces. And here we are quite lucky because the irreducible subspaces are exactly the spaces Kn plus. So basically what we get, that the state after we apply the Haar random unitary is the average state is, regardless of the input, is always block diagonal. So we have no correlations between the photons. And we can directly calculate the rho prime as the projection. And what we get basically is that it's a sum of the blocks that I was mentioning. And each of these blocks is the projector Pn on the subspace of Kn. So this projector, it carries no information about the polarization. And what you can see that there are in a superposition, and the coefficients are exactly the photon numbers. Sorry, oh, something happened. Okay, so the coefficients are exactly the coefficients of the superposition of the photons. Okay, so so what do we actually get from this? So what you can see that the average state, it actually is not fixed. So for different, or let me specify it in the following way. The output state contains no information about the polarization of the photon, and it contains only information about the imprecision of the source. So the only information that is contained there is about the numbers of the photons in the pulse, but it has nothing to do with the information that we are transmitting. Okay, and if you make it more restricted, and these CNs will be the same, so the source will be behaving in the same way for each input state, then we recover the security requirement of the quantum one-time pad, meaning that the output will be the same, the average output will be the same for all inputs. Okay, so this was like the good news. So I already explained that when you take the normal one design, in general, the encryption of quantum information, and you have a multi-photon pulse, it becomes insecure, so it does not randomize multi-photon pulse. But the good news is that we can take a bit larger set of unitaries, infinite in this case, or some approximation, still very large, of the random unitaries, and then it will behave, then it will behave as we want. So it will be able to randomize any multi-photon pulse. But of course, this is highly impractical. So what to do with that? I mean, the straightforward candidate, as you would see, would be to replace the full random unitary with some finite set, and this finite set will be a unitary T design, which still are pretty large, but at least we are getting somewhere with the efficiency. After all, I mean, if you think about it a bit, I mean, the energy of the source is limited. So it's quite, while it might be a bit of a problem or quite limiting, for the experimental setup to say that there will be at least at most one photon, it's quite reasonable to assume that we can put some upper bound, capital N, on the number of photons, okay? So right now we are looking for a channel that on one hand side is more practical to implement, especially it has a finite number of unitaries, as small as possible. And on the same moment, it mimics the behavior of the random unitary, the twill, but only on the subspace, which is a direct sum of the spaces corresponding to up to n photons. And now, since I think it was already quite technical, and I was assuming that the time is limited, I will just tell you the result for the unitary design, because this part is more technical than the previous one, and you can take a look in the paper on the archive if you want the details. So now let's assume that we choose a unitary operator randomly from a unitary N design. Then it is able to secure up to n photon pulse, but only under two assumptions that are a bit surprising, but it is like it is. So if we have only even photon numbers, so 2, 4, 6, 8, then it leaks no information. If we have only odd photon numbers, it also leaks no information. But as soon as we have a pulse where we mix even and odd photon numbers, then the unitary N design is leaking some information about the plain text. So it means, in general, the unitary N design is not an answer to this problem, but perhaps you can still use it because you can do some precautions in the experimental setup that will allow you to use the unitary N design and still maintain the security. So for instance, you have a type 1 spontaneous parametric down conversion source, then it produces the even photon numbers only. So for such a kind of source, you can easily use the N design to encrypt completely any photon pulse with up to n photons. Or you can use a combination of a general multiphoton source with some selective erasure channel that eliminates coherence between the subspaces of different parity, and it keeps the other subspaces undisturbed. So an example can be non-destructive photon number measurement. Okay, so the conclusion is that there is a experimental problem with the encryption of quantum information, much like in the case of QKD, when you have when you are just following the definition of the private quantum channel and you introduce a multiphoton pulse, then such an encryption is not secure anymore. Providing you will be choosing from the full unitary group based on the Haar randomness, then it becomes completely secure for any number for any multiphoton pulse. And in case you want to go efficient, you can use the unitary T designs, but then you have to limit the photon number upper limited by T, or the capital N, as I said before. And you have to make sure that either it produces only state with even photon numbers, or state only with odd photon numbers, or you have to somehow erase the coherences between the subspaces of different parity. Okay, so thank you for attention.
Thank you, Jan. The floor is now open for questions. Please raise your hand. And I must add that if you have questions about encryption in the Kama Sutra, Jan would be happy to take them offline. So.
Oh, okay. Well, actually, I mean, can I just point out that there is nothing inappropriate in this part of Kama Sutra?
Oh, okay.
It doesn't have to be taken
right.
offline. No need for that.
Okay. So please raise your hands if you have any questions. I do not see any hands raised. Maybe it was.
Well, I have raised.
Oh, okay. Yeah, I do. I see. Sorry. Arvind, please go ahead.
Yeah. So, see, we have qubits and we have n photon states. But then if you look at the CV continuous variable QKD protocols, we may even have states which have fluctuating number of photons. So how would we go there when the photon number is not even fixed?
Actually, in this case, it is the same. We are, I mean, I started with the fixed number of photons, but in the end, the derivation is for a mixed photon number. Let me show you. So basically, it's here. So I started with this. So this is where the photon number is equal to n. You have n photons. But in the end, and up to here, it's only n. But here, we start with the completely arbitrary photon number, meaning we are discussing the Hilbert space H. That is a direct sum of the Hilbert spaces of the fixed photon number. So yes, we can have a superposition of photon numbers.
All right. Okay. Maybe I missed that.
Yeah, I mean, it was quite technical. You know.
Soumyakanti?
Yeah, thanks for the talk. You said, I mean, if I extend this analogy between the n number of qubits and the n-dimensional subspace construction in the continuous variable system, so does this map fit equally well in case of entanglement? Like when we have this, I mean, can we analyze this entanglement breaking channel and all other channels in the same form?
Well, the answer is very simple. I'm a computer scientist, and sorry, I have almost no knowledge about the continuous variable systems. Sorry about that. And I can only tell you that I'm trying to improve it soon.
Okay.
Okay. Thomas?
I mean, we are discrete creatures, you know.
Yes, thank you. Yes, I had a similar question, maybe, namely, you know, there are these these nonlinear effects where you know, you multiply the electric field with its complex conjugate, for example, and so, for example, difference frequency generation. And the question is, do you think that your encoding could be hacked by means of such nonlinear effects? Because it might be that you, if both photons are carrying the same U, that you might be able to actually produce from both photons a photon that has a U dagger U. This is basically my question.
I know what you mean, and well, it depends. I mean, if you are talking about using the unitary one design, it means if we just take this private quantum channel, then in principle it can be, well, not exactly produced like exactly, but with the increasing number of copies, and of course, especially when you have a limited set of plain text, you can easily reproduce the original one. But if you are talking about the Haar random, then I really do not see how would you be able to do that, because you are talking about something that you are doing on the side of the eavesdropper, right?
I want to bring two photons together, two photons out of your n photons, and basically let them interact in a nonlinear way in order to resolve the U's that they are carrying. But if each of them is carrying a different U, like in your Haar measure, then of course I can't do it. You know, I can only do it if they all carry the same.
And I assume you are here, right? In the picture. So it's after the encryption.
Oh, sorry, I didn't see your picture. Yeah, yes.
Here,
I'm there.
Here.
So it's encryption, and then I have some extra nonlinear medium, and it merges two photons into one photon, and this one photon is now maybe not carrying the unitary. But in order to do that, I need to have the same unitary in both. Is that so with your Haar measure?
It's solved with the Haar measure, yes. And in the case it's just the normal private quantum channel, then you can get even a higher number of photons. And then, of course, it will be much easier. I don't think you will be able to do it perfectly for two photons only. But for the higher number, I think you can get pretty good approximation of that.
So you're saying I could hack it, or you're saying it's not possible?
If we are using the Haar random, it's not possible. If you are, if you are not using,
because they're all in a different state. I mean, let me understand this Haar. Does it mean each of them is in a different, or is it like a superposition of these states? No, it's a mixture. It's a mixture, right?
It's a mixture. It's a mixture. It's all of them are the same like this, but there are simply too many of them and simply too structured. So in the end, if you take a look at the big density matrix.
Yeah.
And if I take two different input states, make a multiple of them, and take the two big density matrices, then these two matrices will be the same. So you won't be able to do anything.
Got it. Yeah, okay, thank you.
Okay, so there are no more questions. I thank Jan for a wonderful talk. And with this, we close this particular session. I thank both the speakers for keeping to time and for giving very nice talks. It is now my pleasant duty to close the conference with a vote of thanks. I thank the director, Isa Mohali, and the registrar, Isa Mohali, for institutional support. I thank all our eminent speakers from India and all over the world for accepting our invitation and delivering such wonderful talks. I thank all the contributors for putting up such nice posters online. I thank all the participants for being such a great audience. Despite the early or the late hours, you were such an interactive audience that we almost forgot that you were not live. When Sandeep and I began planning for QFTA 2020, we were hoping against hope that the pandemic would play itself out and we'd be able to host all of you physically at Isa Mohali. That didn't happen, and by late August, we kind of knew that we had to plan everything online. And that is when our students stepped in and basically, took over the organization. So now I invite tech gurus of QFTA 2020, Joravar Singh, Jaskaran Singh, Vikash Mittal, and Akshay Gaikwad to please switch on your videos so that everybody can have a look at you. Yeah, I can see Joravar and Jaskaran, Akshay, and Vikash. And
yeah, we are here.
We are here. We are here.
Oh, okay. Okay, great. So I now request the entire QFTA team, my co-conveners and the faculty members of the local organizing committee, and the entire student team to please switch on your videos so that everybody can have a look at all of you. And so we raise a toast with whatever we have. I have a glass of water, and from the entire QFTA team, we wish all of you a very happy.
Okay, it may not look like that, but it's a glass of water as well.
Okay. And
yes.
So yes. And we wish all of you a very happy and healthy 2021. And we say goodbye now, and we hope to see you physically for QFTA 2021 at Isa Mohali. Bye-bye.
Okay, thank you. Bye.
Bye.
Hello, Zora.
Yeah, you guys can have a chill out session. I am logging out now. I have to go get some dinner. Bye, guys.
Bye.
Bye.